the 175 glorious years of GSI. With thematic coverage ranging from critical minerals, tectonics, geohazards, and next generation geophysics to marine systems and geoheritage, this seminar continues to foster a vibrant platform for knowledge exchange and scientific advancements and collaborations. The sessions ahead carry this vision forward, integrating frontier research with informed decision making and collaborative progress. This gathering stands as a testament to our shared commitment to knowledge, discovery, and the ever evolving pursuit of understanding the earth beneath our feet. With renewed enthusiasm, we now move forward into the heart of day's deliberations, enriched by the insights of experts who continue to illuminate our journey. To formally commence our session, it is my distinct honor to invite Dr. Geoff Fraser of Geoscience Australia, who will be joining us virtually for this seminar. It is a privilege to introduce a truly eminent voice in the global geoscience community. Dr. Geoff Fraser is a leading expert in geochronology and isotopic tracer datasets and serves as the section leader, geochronology and stratigraphy at Geoscience Australia. He is a key contributor to the development of Isotopic Atlas of Australia and works closely with the renowned Geoscience Australia Shrimp Laboratory, well known for its pioneering UPB geochronology and its crucial role in the long-term distribution of the Temora 2 reference zircon for ion microprobe analysis. Dr. Fraser's extensive publication record stands as a testament to his deep scientific contributions. Sir currently serves as the chair of Oversight Panel for the OSCOPE National Argon Map NAM initiative. GSI shares a long-standing, fruitful, and cordial collaboration with him and the Geoscience Australia, a partnership we deeply value. Ladies and gentlemen, please join me in warmly welcoming Dr. Geoff Fraser to deliver his plenary address. Sir, over to you.
Thank you very much. Let me just share my screen and make sure that's working for you at your end. Can you let me know if my screen is being shared successfully?
Yes, sir.
Very good. Well, thank you very much for that introduction, and good afternoon from Canberra, Australia. It really is a pleasure to be able to join you online, and I'm just sorry that I'm not able to be there in person in Jaipur. I'll be talking today about age and isotopic mapping from the perspective of how we have been doing this at Geoscience Australia. An overarching theme of this presentation is the importance of geological time as an aid to geological mapping and in guiding resource exploration, and hence age and isotopic mapping as an important role for a national geological survey organisation. Just let me make sure my slides are going to advance. Whoops. Okay, I want to acknowledge that the opportunity for me to speak here today has arisen largely out of interactions between Geoscience Australia and the Geological Survey of India over approximately the last 10 years or so, which were conducted under a memorandum of understanding in which GA and GSI have conducted numerous discipline-based workshops and have hosted secondments of staff. And I'd like to thank everyone involved, both at Geoscience Australia and at GSI, for making these interactions so successful and enjoyable. These interactions have had tangible scientific and technical benefits, but personally I'm also confident that they've had equally important and slightly more intangible benefits in creating friendships and understandings between Australia and India, and I'm very grateful to have been a part of that. So congratulations to the Geological Survey of India for reaching this milestone of 175 years. This makes GSI one of the oldest national government science agencies in the world, perhaps preceded only by Britain, France and Canada. And certainly the GSI is a lot older than Geoscience Australia, where I work. which was only established as a national geological agency after the Second World War in 1946. So this milestone of 175 years as a National Geological Survey caused me to reflect on the fundamental role of geological surveys and where did they originate. And I suspect that geological surveys really owe their existence to the development of the concepts of geological mapping. And modern geological mapping is really not much older than the Geological Survey of India. I think it's widely accepted that the first modern geological map was the mapping done in the United Kingdom by William Smith, published in 1815. And you see a beautiful image of that map here on the screen. So the publication of this map is only roughly 35 years before the establishment of the Geological Survey of India. And the story of the development of this first modern geological map is wonderfully told in the book by Simon Winchester. You see a title page on the left of this image. This book called The Map That Changed the World. And those of us who've spent our lives working in geological surveys take it for granted that geological mapping is fundamentally valuable. But such maps didn't really exist prior to this work by William Smith. And without geological mapping, what would a geological survey do? What was so fundamental about this work of William Smith? He recognised that there are systematic patterns in the sequence of rocks that he could see, primarily, in his case, looking at sedimentary rocks. And he did this by very careful recognition of changes in fossil assemblages in different layers of rock, and that these characteristic fossil assemblages are found consistently across the country. Once again, this is something that we largely take for granted today, but at the time this was a fundamental observation. And remember that this observation was made before Darwin's theory of evolution was developed. So there was, at that time, no real theoretical reason to expect such systematic patterns to be repeated throughout the countryside. But nevertheless, William Smith's observations, made via his work as a canal engineer, provided a basis for him to be able to correlate stratigraphy across the country and map out patterns of rock. And very importantly, his recognition of stratigraphy allowed him to predict what rocks would be present beneath the ground in different parts of the country, based on what he could see near the surface. And he could also equally predict what rocks would not be found at depth. Why was this useful? Well, William Smith was working during the Industrial Revolution when demand for coal was skyrocketing as a source of power. Exploration for new deposits of coal was going on around Britain, but without geological maps, the success of this exploration was very hit and miss. William Smith understood the predictive power of his geological maps. He could see that many people were looking for coal in the wrong parts of the country, and he could predict that they were going to fail. In fact, he publicly commented on how much money was being wasted looking for coal in the wrong places. Why am I talking so much about William Smith and fossil assemblages and coal exploration in a presentation about age and isotopic mapping? Well, I think there are numerous interesting parallel threads that are relevant to the work of geological surveys today. For one thing, we're again in an age where there's increasing demand for mineral resources, in this case to power an energy transition towards electrification and lower greenhouse gas emissions. In our case, those mineral resources are the so-called critical minerals, as well as a greater diversity of metals required in modern technologies. So governments are looking to geological surveys and their predictive maps to help guide successful resource exploration. Underlying the approach of William Smith was the record of geological time, represented in his case by the changing fossil assemblages in sedimentary rocks. This indirect record of time is what gave him the ability to correlate rocks over large distances and help make regional or national maps. Similarly, my topic today, age and isotopic mapping, is founded on having a measure of time. For William Smith, his measure of time, that is fossils, was recorded only in sedimentary rocks. And we also now know that the fossil record really only works for the past approximately 500 million years. That's approximately 1/9 of the geological history of Earth. And the fossil approach also works only in sedimentary rocks. So for the other 8/9 of Earth history, and for correlations of igneous and metamorphic rocks, we need another measure of time to make our correlations that in turn allow us to develop time-based geological mapping and the predictive power that comes with it. And of course today, that measure of time is based on radioactive decay. This is a process that was discovered only in the late 1800s, almost 100 years after the work of William Smith, and about 50 years after the establishment of GSI. I still find it remarkable how quickly the discoverers of radioactivity recognised that it could be applied to the dating of rocks. Less than a decade after the discovery of radioactivity in 1896 by Henri Becquerel, Ernest Rutherford was making the first attempts to use radioactivity as a means of measuring geological ages. Of course, the techniques have come a long way since then, but even those early pioneers could see the potential. All this introductory context is really just to make the point that geochronology and isotopic mapping methods are fundamental to our understanding of most of Earth history and to our ability to make useful and predictive correlations and geological maps. And hence, these tools have a fundamental place within the activities of a modern geological survey. And from here, I want to move on to summarise how we've been developing and using age and isotopic maps at Geoscience Australia. Firstly, we don't do age and isotopic mapping in isolation. It's part of a broader suite of mapping and data collection designed to characterise the continent at a range of scales and depths. So on the left-hand side of this image, you see a series of national scale geological maps based on different geological time slices which broadly correspond to different depths. On the right, we have an image showing the distribution of major known mineral deposits across Australia. And you can, these are these symbols, the brightly coloured symbols of different shapes. You can see they're not uniformly distributed across the continent. They occur in clumps or groupings according to the geology, as you'd expect. And later in the talk, we'll also see that the deposits are clustered in time as well as in space. Another thing to note on this map of mineral deposits across Australia is the very large regions where there are no discovered major mineral deposits, at least not discovered so far. And this is largely because in those regions, the rocks that might host those deposits do not crop out at the surface. In those parts of much of the interior of Australia, the landscape may look like this photo, where there are no rocks to be seen at the surface. It's covered in sand and desert dunes and soils. And this clearly represents a great challenge for mineral exploration. But it's also a great opportunity for us within geological surveys and within the exploration industry to help the discovery of new resources if we can be predictive about guiding effective mineral exploration in these challenging covered regions. So in mapping undercover, geophysical methods are key tools, and we are progressively improving our national coverages of various types of geophysics. As you see on the left, the magnetic coverage, on the right, the gravity coverage. And these national scale coverages are built up by stitching together hundreds of more local surveys and levelling them into a national picture. Similarly, we're mapping out other physical properties of the continent, in this case seismic velocity, with a program of passive seismic sensors across the country that we call AusArray. Equally, we're mapping out electrical conductivity at depth within the Australian continent, in this case using magnetotelluric techniques in a national scale program that we call AusLAMP. And this is again producing wonderfully interesting images of the deep crust and its electrical conductivity structure. And all these geophysical tools are fantastic, and they're allowing us to build up new views of the continent that can be visualised in 3 dimensions or in cross sections and they really complement our traditional geological maps. And in turn, those geophysical models and images can be used to make geological interpretations. In this case, we're looking at a 3D interpretation of major crustal boundaries in Australia, or essentially the big bounding structures, deep shear zones and so on. But all these images that I've just quickly showed you, as great as they are, they also have something in common, which is something of a limitation. And that is that they are snapshots of the continent in its present day configuration. But we know that our geological history and much of our mineralisation occurred hundreds of millions of years ago, or even billions of years ago. And this is clearly where age and isotopic mapping can help us. It can help by adding a time dimension to our understanding of these modern day images of the crust. And in that way, it helps add extra predictive power in our search for new resources. So at Geoscience Australia, we've developed this concept of an isotopic atlas, where we collate a series of thematic isotopic coverages based on different isotopic methods or from different types of sample materials. And in the stack of map images that you see in the middle of this slide, you can see from the top we've got geochronology layer, strontium and lead isotopes in surface materials, lead isotopes from mineralised ores, lutetium hafnium isotopes from zircon, and the lowermost image, samarium neodymium isotopes from whole rocks. And you can see that the different layers of maps here, or if you like, the different pages in the isotopic atlas, they're all in different stages of completeness or spatial resolution. So this is ongoing work, but in the next few slides, I'll show a few examples of how these various isotopic maps are being created and used. So perhaps the most fundamental data set is the geochronology of minerals and rocks. And what I'm showing here is the geochronology layer from our online GA portal. And in this layer, we've compiled well over 7,000 geological ages and delivered them in a consistent online format. And building up this scale of data set requires careful measurements at an individual sample level, sample by sample. So it takes a long time, and the national coverage represents several decades worth of work. And we continue to build up this national coverage via new geochronology measurements using our in-house shrimp instrument at Geoscience Australia. You see a picture of the shrimp here, sensitive high-resolution ion microprobe. For those who are not familiar, this is essentially just a very large mass spectrometer, and it's able to make very tiny measurements of portions of individual mineral grains. So the scale in the image on the right, the blue and red dots are indications of the spot size of the shrimp at about 20 microns. So for us, much of this geochronology, it doesn't happen directly at the national scale. It happens at local to regional scale via collaborative projects, either with our regional geology teams or with partners from our state and territory geological surveys around Australia. And so suites of measurements are put together and published in reports and papers, and they're very useful products on their own, but all the data then feeds into progressively building that national coverage. Now, having this consistently compiled national coverage gives us the option to do some thematic visualizations, I guess, of the geological evolution of the country. So what I'm going to play here now is a short video that we've put out. It's available on YouTube, and it shows the magmatic history of Australia through time. Essentially, we're just showing the geochronology from magmatic rocks across Australia. So shortly, you'll start seeing the sample points appearing in time order. So from about 3.5 billion years ago. There's a few things to notice as we watch this. You'll see there's a distinct age progression, with the oldest rocks being in the west in our cratons of the Pilbara and Yilgarn, as you see at the moment. And progressively, you'll see the patterns build up towards the east. You'll also notice that there are long periods where not very much happens, and then shorter periods where a great deal of magmatism happens, which is just emphasising the episodic nature of the geological history. Here we see the Proterozoic belts of Central Australia being represented by all the magmatism through this central part of the country. And we'll shortly go through another period of relatively quiet period in terms of magmatism before Eastern Australia starts getting built on and accreted to the Precambrian part of Australia. So there you see in about a 1 minute a quick snapshot of the magmatic history of Australia based on thousands of data points. And we've done a similar thing with visualising the mineralisation history of Australia, and we've put out a complimentary YouTube video for that, and you can find that via the link that's on the screen there. I don't really have time to play that here in this presentation, but this is simply a screenshot from that video that's showing the progressive development of different styles of mineral deposit through time across Australia. And we can also depict that information about the mineral deposits through time in other ways, like as we're showing here, in terms of time-space plots. And very quickly, to summarise, we've got the Archean parts of Australia, primarily in Western Australia, on the left part of this diagram, various different mineral deposits depicted by the different coloured and shaped symbols. And then through the Central Australian belts, the Proterozoic evolution of Australia in the central panel, and then the younger Phanerozoic belts of Eastern Australia on the right-hand panel with their mineral deposits. And again, you can see that there are definitely, it's a very episodic history of development of mineral deposits. In addition to measuring the ages of processes like magmatism and mineralisation, we can also use other isotopic traces to reveal other aspects of the continent's evolution. And in this case, we're looking at a map of neodymium model ages from felsic igneous rocks across the country. Essentially, these are showing us the timing of bulk crustal growth across the continent. And again, we can see a strong age progression, as you'd expect, with the oldest material in the west in the sort of light, sort of cream and brown colours, through the Proterozoic of Central Australia, and then the younger terrains of Australia in the east in the yellows and greens. So the same neodymium map that I just showed you can also be used at regional or craton scale as a guide to mineral fertility. And this example comes from the Yilgarn Craton of Western Australia. This craton, as I think many people would know, it's richly endowed with gold and nickel, but those mineral deposits are not uniformly distributed across the craton. And you can see in the central upper panel, the neodymium model age in the background, with the older craton in the west, shown in the yellow and brown colours, and the younger or more juvenile part of the craton, shown in the east, in the green colours. And the red dots on top of the isotopic map are the distribution of gold deposits. And you can see that there are a lot more deposits in the juvenile or eastern part of the craton, in the isotopically green areas on this map. And you can do a similar thing with nickel deposits, shown in the lower panel here. Again, we're looking at the same neodymium isotopic map of the Yilgarn Craton, with the nickel deposits plotted as the blue triangles. And you can see the nickel deposits are very strongly aligned along the boundary between the old part of the craton and the younger part. So showing us that the isotopic mapping is helping us map out some fundamental aspects of the craton that have also played a part in controlling the distribution of mineral deposits. So it's the success of that type of application that really led us to scale up the mapping of neodymium isotopes across the whole country so we could do similar things in other places. And very similarly to neodymium, but with a different isotopic system, the lutetium-hafnium system in zircon, we can also do similar sorts of things. In this case, this example comes from southeastern Australia, where we're essentially mapping out the boundary of the Precambrian part of Australia with the younger accreted Phanerozoic Australia. So on this map, the colour scheme is the older parts of the Gawler Craton here are shown in the purples, and then the younger accreted or Phanerozoic terrains are in the green and yellow. And you can also start to see, you can see the nature of the edge of Precambrian Australia. You can start to get a sense of perhaps there are ribbons of extended protonic material buried beneath parts of eastern Australia, shown by this, I guess, sinuous purple band. So this is another application of isotopes to show us the crustal architecture, and that in turn can be related to the prospectivity for different sorts of mineral deposits. We've also used these isotopic maps as a guide to developing the major crustal boundaries coverage that I showed in 3 dimensions earlier in the talk. So here we're looking again at the neodymium model age map of Australia, and the red lines are an interpretation of the major crustal boundaries, which are in part informed by the isotopic patterns. But not only that, these crustal boundaries are also being developed based on interpretations of reflection seismic information, other gravity and magnetics and other geophysics, and all the geological information that we have. And these crustal boundaries are obviously helping us understand the fundamental building blocks of our continent, but they're also places where mineralizing fluids can be channeled along these boundaries. So they're important from a mineral systems perspective as well. And so this coverage of major crustal boundaries, informed by the isotopic mapping, is a very important input into our predictive maps for mineral prospectivity. And the image on the right shows us an example of a recently released predictive map of the prospectivity for iron oxide copper gold in Australia. And we have a series of these maps for different styles of mineral system, and we're continually trying to improve these and produce them for a wider range of mineral systems. So to start summing up, I've already made the point that the age and isotopic data that underpin these various maps and interpretations are available via the online GA portal. In that platform, the data can be filtered and subsetted as people would like to do, and then downloaded in multiple different formats if people want to take it offline and do other things with it. So the key messages I guess I want you to take away is that we've been gradually building up multiple age and isotopic data sets at national scale. In several cases, we now have sufficient data coverage at that national scale to make meaningful maps. Those data sets are available freely from the GA portal, and they provide very complementary understanding and images to complement our geological and geophysical maps and models. They provide insights into crustal architecture and evolution, and they provide important inputs into guiding mineral prospectivity analyses. And we recognise that there's a lot of scope to improve the geographic coverage of our maps and to produce a wider diversity of isotopic coverages or from a wider diversity of sample types. And there's more that we can do, I think, in the future to more quantitatively correlate the insights from the isotopic maps with geophysical and geochemical data. And that's work for the future. I'd like to re-emphasise that a lot of this work that we do at Geoscience Australia is done in collaboration with our state and territory geological survey partners, and we thank them for their part in all of this. It's a national collaborative effort. And it also involves partnerships with several academic groups and other government geoscience agencies. So again, acknowledgements to them. And I've included a list of references here that may be of interest if you want to follow up in more detail about some aspects. But as a final word, returning to our theme from the beginning of the talk, I hope I've been able to present a case that a measure of geological time is a fundamental part of the predictive power of geological mapping, and show you that how a systematic program of geochronology and isotopic mapping is a natural complement to geological and geophysical mapping, and it's therefore a natural part of the work of a modern geological survey. And we can look back at the pioneering work of William Smith that paved the way for geological mapping and his map that changed the world, and perhaps suggest that modern applications of geochronology and isotopic mapping can also produce maps that might change our world, or at least change our understanding of that world. So thank you again for the opportunity to speak at this milestone event today. And once again, I'd like to congratulate Geological Survey of India for reaching their 175th anniversary. Congratulations, and hello to all my GSI friends online. Thank you very much.
Thank you, sir. A heartfelt thanks, sir. Sir, thank you for making it possible to join us here and for your inspiring and illuminating words.
Would you like me to stop sharing my screen now?
Sir, I think that would be fine. I'm sure your words would guide and motivate us in the future. Also, this is an announcement that we'll not be opening the floor for questions. The audience may hold their questions for the end of the seminar. We'll communicate your questions directly to Dr. Fraser. So thank you so much. Thank you so once again.
Thank you for the opportunity.
Moving on to the next session, moving on to the next plenary talk of the day, it is my honor to introduce our distinguished speaker, Professor Emmanuel John Carenza, one of the world's leading authorities in mineral prospectivity analysis, mineral exploration, geochemistry, and spatial predictive modeling. Professor Carenza began his career as an exploration geologist and geochemist at the Mines and Geosciences Bureau in the Philippines. He then completed his PhD, specializing in mineral potential mapping, a field in which he has since become one of the foremost global experts. His academic journey has taken him across the world. He now serves as Professor of Economic Geology at the University of the Free State, continuing to advance research and mentorship in various fields. His extensive work has already been cited in around 22,000 papers till date, and the figure is ever growing. Professor Carenza currently serves as Editor-in-Chief of Natural Resource Research and Associate Editor of Ore Geology Reviews and the Journal of Geochemical Exploration. Ladies and gentlemen, may I request your attention to the screen as we extend a warm welcome to a distinguished scholar and a globally renowned leader in mineral exploration science, Professor Emmanuel John Carenza. Sir.
Good afternoon to all of you there. Can you hear me?
Yes, sir.
Yes, sir, you are very much audible, sir. You may continue.
Okay. So again, good afternoon to all of you there in Jaipur, India, and congratulations to the Geological Survey of India for your 175 years of glorious service. And thank you for having me. It's a pity that I'm unable to be present there physically, but I am pleased to give a small contribution to your international seminar. So my presentation has two parts. Let me So my presentation has two parts. In the first part, I'll be talking about different branches or types of artificial intelligence and how they developed in mineral exploration targeting. And the second one part, a smaller, shorter part, is a short case study on how we can use artificial intelligence to delineate exploration targets. Um, the first part is actually, you might be interested, is a talk that the European Geological Survey directors have asked me to present to them last year. And the one that I'm giving you here is a modified version of that. So just to begin with some definitions, artificial intelligence is the science of making machines. That means computer algorithms that can think like we do. And this hope that this AI can do things that are smart, at least not smarter than we are. And it's a technology that can process large amounts of data. So this is the key word here. We use AI if we are, need to analyze large amounts of data. And the goal, of course, is to be able to recognize complex patterns from huge amounts of data. And we humans aren't able to do that. So we need the help of AIs. So AI leverages on machines to mimic the problem solving and decision making capabilities of the human mind. Now, why should we use AI in mineral exploration targeting? Well, to understand that, we need to know what mineral exploration is. I think many of you, all of us know, but I like this definition from the Geological Survey of Ireland, that mineral exploration is the process of searching for evidence of any mineralization hosted in the surrounding rocks. So what's the problem? The problem is to find evidence of mineralization. It's not easy. Well, if it is easy, then we could have discovered all the deposits on the Earth's crust. But up to now, we haven't done that. So once we have found an evidence, there are many decisions to be made. And this, again, needs a lot of data. We need to decide which evidence to follow up, which evidence is more important than the other, and which areas with evidence should be prioritized for further exploration. And yeah, all these problems and decisions to be made need data, huge data, and so we need AI. Now, there are different branches or types of AI that have been used in mineral exploration targeting, and these are listed in the screen. At least these are the ones I know. I hope I know everything, but yeah, you never know. And I will be talking each one of these in the following slides. So let's go first with expert systems. An expert system is designed to solve complex, nonlinear problems. So I highlight nonlinear because many of our relationships that we are looking at actually are nonlinear. And for us, we were trained to think linearly, but computers can look for this nonlinear relationship. So an expert system is a computer program that uses AI technologies to simulate the judgment and behavior of humans that have expertise and experience in a particular field. So in this case, mineral exploration, targeting. Now, expert systems are usually intended to complement and not to replace human experts. Now, the first expert systems were created in the 1970s, and they proliferated in the 1980s. These were among the first truly successful forms of AI. Now, an AI has two subsystems, a knowledge base that represents facts and rules, and an inference engine that applies those rules to known facts or data to be able to deduce or discover new information. Just very quickly, here's an example of a simple inference engine to map prospectivity for porphyry copper. The first maps on the tabs are three maps are combined according to a certain logical operator, which produces new information. In this case, zones where porphyry plutons may be in place. The last two maps are combined again with another suitable operator, to deduce new information about zones of hydrothermal systems. Or when we combine these two new derived information with a suitable operator, we can map zones where porphyry potential can be found. Now, how did the developments in export system develop? Here I look at the number of publications and plot that versus the years. Now, this part of the graph here is related to the development of an expert system called Prospector. This expert system were developed by guys in Stanford University, and this was able to successfully identify the location of an undiscovered porphyry molybdenum deposit. But unfortunately, this is the only paper that documents that successful discovery. Maybe they have discovered further other deposits, but those were not documented or published. Let's go to fuzzy logic. This is an approach to variable or data processing that allows for multiple possible truths. So the expert system and fuzzy logic are AIs that can be used to represent knowledge. Okay. So the traditional way to represent evidence is a Boolean logic way. So either we have the presence or absence of an evidence or predictor, but with fuzzy logic, we can have a range of degrees or presence or absence of an evidence, which is more realistic than the Boolean way. So fuzzy logic attempts to solve also nonlinear problems with an open, imprecise spectrum of data and heuristics that make it possible for us to obtain an array of accurate conclusions. So like an expert system, it also has a knowledge base and an inference engine. This graph shows how the application of fuzzy logic to mineral exploration has developed throughout the years. And this part of the graph here is related to the developments in GIS. So with the advent of GIS, the application of fuzzy logic has become quite easy. And that's why we have a growing number of papers or research on the application of fuzzy logic to mineral exploration targeting. Now we move on to to machine learning. It's a branch of AI and computer science. So now we marry AI and computer science that focuses on the use of data and algorithms to imitate the way we learn, and gradually improving its accuracy. It involves the use of computer systems to analyze complex, nonlinear spatial relationships of deposits and certain predictors or evidence. On the other hand, a deep learning is a method in AI that teaches computers to process data in a way inspired by the human brain. So, deep learning is a type of machine learning based on artificial neural networks. There are many types of machine learning, but deep learning is just based on artificial neural networks. It is also designed to analyze complex non-linear relationships. So what's the difference between ML, machine learning, and deep learning? Okay. It's that deep learning is a specialized subset of machine learning that uses artificial neural networks with more layers than a typical artificial neural network. So we call this deep neural networks. The last type of AI that has been used in exploration targeting, and its application is still in its infancy, is natural language processing. It has the ability to understand human language as it is spoken or written, and so it is referred to as a natural language. It uses machine learning, not deep learning, to process and interpret text and data. So if you look at how machine learning developed, it has its application to mineral exploration started just about a decade ago. okay, from 2015 up to now, but it has been tremendously developed in the last few years. And this is due to the rapid developments in software programming and computing capabilities. Likewise, with deep learning, it has developed about just 5 years ago. And also this is due to the rapid developments in software programming and computing capabilities. Now, NLP, or natural language processing, is a new application of AI, and most of the research done so far in its application has been done by geological surveys. In this case, for example, Geological Survey of Canada, the USGS, and also collaboration with Geoscience Australia. This is one example, and this is another example done by the Geological Survey of Canada and with collaborations from the academia. So this is probably one type of AI that the Geological Survey of India can embrace in its future work. Now, if we put all those graphs together, we can see that the applications of machine learning and deep learning has outnumbered the applications of expert systems and fuzzy logic. And the growth in the applications of machine learning and deep learning is still growing. Now, these types of AI that have been used in mineral exploration have all been used in an activity that we call mineral prospectivity mapping, MPM in short. And this activity supports mineral exploration targeting. Mineral prospectivity modeling is the activity that quantifies the likelihood of where mineral deposits may be found. It is synonymous with the term mineral potential modeling, which quantifies the likelihood of where mineral deposits may be contained in an area. So these two terms, once you find this in the literature, are synonymous and they are actually interchanged. We also interchange the term modeling and mapping because a map is a model. This is the workflow of mineral prospectivity modeling. Okay? And this can be found in my book, which I published in 2008. The workflow starts with a conceptual modeling of mineral prospectivity, which describes theoretical relationships between various factors or controls of how and where certain types of deposits are formed. Okay? I highlighted how and where because the how relates to the process, and where we need to know where these deposits can be found. Once we have established that conceptual model prospectivity, we can gather suitable data, put that in a database, and we can play with the predictive model parameters. In some cases, this analysis of predictive model parameters provides feedback to conceptual modeling because the data may tell us something else than what we know theoretically. So we can update our conceptual model. And once we are satisfied, we can create predictor maps, which can be combined according to a variety of integration models. Nowadays, we use AI as integration models, and then we create a prospectivity map, which need to be validated. So we need to realize that this workflow is garbage in, garbage out, which means that if the conceptual model is wrong, then the output predictive model of prospectivity is meaningless and should not be used to guide exploration. So this is where the geologist comes in. And the part that I highlighted in green is the part of the workflow where AIs can be used. And for this part, we can ask data scientists or computer scientists to help us. But this part here is the realm of geologists. Now, the earliest works on mineral prospectivity mapping made use of mineral deposit models to develop conceptual models of prospectivity. In recent works, this is based on mineral systems concept. What's the mineral system concept? This has been introduced by the Australians in the late 90s. And basically, it tells us that to develop mineral prospectivity models, we need to consider four main processes and represent them in the model. Those are the process related to the source of energy, source of fluid or metal, and then processes related to the transport of the fluids and metals, and therefore we need also processes related to pathways. And finally, we need to model processes related to trapping mechanisms. So with all these four major processes, uh, the deposit should be able to be formed, and therefore we can model prospectivity where they are formed. Now, again, if we look at the developments in AI in mineral prospectivity mapping, it is similar to the graph which I showed you earlier, which is which is about mineral exploration. And again, the applications of AI to MPM is still developing and has outnumbered the use of expert systems and fuzzy logic. Looking at the countries that made use of AIs in mineral exploration targeting, and this is taken lead by China, Canada, and Australia. And India is here, so it uses AI. It has used AI in mineral exploration. But if we look at which countries used AIs in mineral prospectivity mapping, then we don't see India in the top. But again, we have China, Canada, and Australia as the leading countries using AI in mineral prospectivity mapping. Now we ask ourselves, can GIS or AI-driven prospectivity mapping impact metal production? Now to answer this question, I borrowed this graph from Wikipedia, which shows the tons of gold produced since the 1960s up to recently. And this graph is dominated by South Africa. We all know that South Africa is very rich in gold, or used to be very rich in gold. And as we see that since the 1970s, the gold production, therefore the gold deposits in South Africa has depleted since that time. But since the 1980s, other countries have started producing gold in quite large quantities. Now, what happened in the 1980s? This is the year around when GIS-based mineral prospectivity mapping started. And yeah, it's sad to say that South Africa did not embrace this technology while other countries have done. Now, if I use this graph, the number of papers on mineral prospectivity mapping per year, we see a clear trend of increasing research. Okay. For example, in 1985, that's the first paper on weights of evidence, and there are 3 textbooks there. This is a textbook from Bonham Carter, from Pan and Harris, and textbook from myself. And if we put this graph together, we see a positive correlation on the metal production from these countries, from China, Australia, and the US, but the negative correlation with the production of gold in South Africa. So, well, we can make many deductions from this. Well, one of them is that GIS or AI-based mineral potential mapping leads to deposit discovery, which can lead to metal production. So we see the importance of using this technology to help us with mineral exploration targeting. So just some final remarks on this part 1. As mineral exploration targeting proceeds deeper and deeper, we need more and more exploration data. And recognizing deposit-related anomalies or modeling of prospectivity from huge or big data will become more and more challenging, justifying the need to use AI, especially machine learning and deep learning. Research on the use of AI in exploration targeting worldwide is still growing, and India has a lot to do to catch up with the leaders, China, Canada, and Australia, with regards to research on the use of AI in mineral exploration. Now, the use of this technology produces uncertainty, and this topic of uncertainty will become an increasingly hot topic in the years to come. Okay, now I proceed to the second part, where I will show an example of how we can use AI for expression targeting. And I acknowledge here my co-authors here. And actually, this is based on a paper that we published 2 years ago in Computers Enjoy Sciences. So if you miss some details in my talk, feel free to look for this paper or email me and I can give you a copy. So what's the motivation for this case study? Most techniques of geochemical anomaly mapping depend on idealized assumptions about the probability distributions of the data, whether they are Gaussian or multivariate Gaussian or whatever type of distribution. But geochemical data distributions are often characterized by non-linearity and non-stationary properties. And since about 10 years ago, or more or less, machine learning algorithms have been used for geochemical anomaly mapping to avoid parametric statistical assumptions about the unknown probability distributions of geochemical data, and therefore it allows us to model complex geochemical anomaly patterns. And more recently, deep learning methods have been used to recognize complex anomaly patterns in nonlinear Earth systems. And particularly one type of deep learning called the deep autoencoder network has become a dominant method for recognizing geochemical anomalies linked to mineralization. So if we train a DAN, or deep artificial autoencoder network, multi-element geochemical background can be learned by higher level depictions of input signals. So these are signals from the data, furnishing important indications for quantifying reconstruction errors. So reconstruction errors are similar to what we know as residuals or geochemical residuals, which are important guides to mineralization. Now, the ability of the DAN, or deep autoencoder network, to learn geochemical background could be stifled by superfluous joint information, so correlated data, or assorted information from elemental values due to a variety of processes. So we know that mineralization is just one of the processes that can be found in data. Most of them are background processes. Now, to address those concerns, we propose a novel deep learning architecture, which we call InfoMax DAN, which connects the InfoMax, or information maximization, to a deep autoencoder network. The InfoMax DAN is demonstrated in an area, small area in Iran, the Moluman district, to assess its usefulness. And that's what I'm going to show here. This is the area in north of Iran. The area is mainly underlain by intrusives covered by younger quaternary sediments. Mineralization is related mainly to these three lithologies of Paleogene age. As you can see here, so this is topographic high with all these intrusions and where the deposits are, and some are outcropping here.
Sorry to intervene, sir, but our next speaker has
So in
already
this data, my
joined, so we
Iranian
might
colleagues,
ask
they
you
collected
to
composite
kindly
stream
sum
sediment
this up.
samples. Oh, okay.
Sir, sorry to intervene,
Yes.
sir, but as our next speaker has already joined and we are advised to strictly adhere to the schedule, I might ask you to kindly sum this up.
Okay. So I'll go straight to the. So this is the result of the application. So we see some anomalies here which are related to mineralization. We know that this is a false anomaly, a seepage anomaly. But if we don't use the InfoMax, then we miss many anomalies. Okay? That's why we need to use the InfoMax DAN. Okay, this is just a graph showing that InfoMax is better than the standalone DAN. And also this graph shows similar information. And finally, we're able to delineate exploration targets from this map. Okay, so just a conclusion. By using the InfoMax DAN algorithm, the information from original multi-element data can be enhanced so that higher level representations of background could be reconstructed effectively, allowing us for improved recovery of complex anomaly patterns. And compared to a standalone DAN, the InfoMax DAN is better. Thank you.
We are honored to have heard from you, sir. Thank you so much for this insightful talk and sharing your expertise with us. Thank you, sir.
Thank you.
Continuing with our plenary sessions, it is my great pleasure to introduce our next speaker, who is a world-renowned expert in Himalayan tectonics and sedimentation, Professor Yani Najman of the University of Lancaster, UK. With a distinguished academic career spanning over decades, Professor Najman has held positions from lectureship to professorship at Lancaster and has been recognized with prestigious fellowships. She has led numerous international research papers, collaborated globally, and has received an extensive record of highly cited publications. Today, Professor Najman will be delivering her talk on the use of sedimentary records to unravel Himalayan evolution through the virtual mode. I request you all to kindly direct your attention to the screen. Please join me in giving a warm welcome to Professor Najman.
Thank you very much. Can you hear me?
Yes, ma'am, you're audible. You may continue.
Can you hear me?
Yes, ma'am, I can hear you. We all can hear you. You may continue.
Okay, then I shall share my screen.
Yes, ma'am.
Okay, and now do you see my PowerPoint presentation? Could you confirm that you can see my PowerPoint presentation, please?
Not yet, ma'am.
Not yet, ma'am.
No, okay, I'll try again. I'm pressing Window, Share. There we go, how about that? Can you see that?
I guess we are about. Yes, ma'am. Now it's visible.
Okay, so firstly, thank you so much for inviting me to virtually attend your conference. It's a great honor for me to attend. As I said, as I was introduced, I'm going to talk about use of the detrital approach to document orogenic evolution. And I'm going to give you a case study from the Himalayas. Well, the detrital approach is when we use the sediment record to try and document what happens in the hinterland rather than going to bedrocks of the hinterland itself. And why do we do this? Well, the advantage of this, it's complementary to bedrock studies. Bedrock studies can be the information from them, from metamorphic rocks, for example, can often be overprinted in the mountain belt itself due to tectonism or overprinted by later metamorphism or removed by tectonics or erosion. So when that happens, the only remaining record can remain in sedimentary rocks that have been eroded from the mountain belt and then transported and deposited in basins away from the mountain belt, so they've escaped the metamorphism that might have happened in the origin itself. So it's a complementary approach to bedrock studies. So the example I'm going to talk about today is how we use the detrital record to determine the timing of closure of Tethys and the India-Asia collision. I'm just going to put a pointer on, laser pointer, here we go. And I'm going to say how we, or show you how we can use the detrital record to constrain the time of this India-Asia collision using the sedimentary archive that's preserved in the Himalayan suture zone. So as I'm sure you're all aware in this audience, here I've illustrated India coming north, crossing the Tethys, and then colliding with Asia. And we want to work out what time that collision occurred. So just a brief recap. I'm sure most people in this audience will be very aware of the geology of the Himalayas, seeing as how it's spreading across India. But just to recap, we have in brown this suture zone, oh, sorry, not in brown, in green, we have suture zone, which separates Asia to the north from the Indian plate to the south. And on the Asian plate, we have the Gangdesi or Trans-Himalaya, which is a batholith representing the pre-collisional subduction batholith as the Tethys Ocean was being subducted beneath Asia. And then to its north, we have the Central Lhasa magmatic belt and the Karakoram. And then squeezed in the suture zone in the west, separating Asia from India, here we have in purple, the Kohistan-Ladakh Island Arc. And then to the south, we have the various units of the Indian plate. We have the Tethyan Himalaya, the higher Himalaya, the lesser Himalaya, and the sub-Himalaya. And if we look at the pre-collisional configuration, we have Asia to the north, including the Karakoram. We have India to the south, and in the Tethys Ocean that separates the two continents, we have this Kohistan-Ladakh Island Arc, which is this purple unit here. Now here, from the pre-collisional configuration, we're going on to the post-collisional configuration. Now, in the traditional model, this Kohistan-Ladakh Island Arc hit Asia before it hits India. So we've got the Kohistan-Ladakh Island Arc, and this ocean has now closed. We've hit Asia, but the Tethys Ocean between the arc and Asia and India is still open. And then stage 2, India collides with this Asia plus arc at a later point. And people have dated this Asia plus arc conjoined collision with India, so the terminal collision, in a number of ways. For example, 55 million years ago, based on eclogites indicating the first India-Asia contact, that's de Segoya et al. We have 50 million year time, which is the marine retreat in the suture zone, that's Green et al. 2008. And what we're more interested in, as it's the detrital approach, is 50 million years ago, which is the first time that people have seen material from this Asian plate on the Indian plate. So material eroded from Asia, landed on India. That's first found in the sedimentary record in India about 50 million years ago. And that indicates that Asia must have collided with India by that time in order for the material to cross the ocean, which is no longer there, and land in India. And that's, for example, the work of Clift et al. Now, in order to be able to determine when Asian material lands on India, we have to have an Asian material that is different and diagnostic from India. And we use zircon uranium lead ages, detrital zircon uranium lead ages. We have Gangdesi here, which was Asia. We have the Kohistan-Ladakh Island Arc signature, and we have the Indian signature. And what you can see is that the Trans-Himalaya or Asian plate and the Kohistan-Ladakh Island Arc both are dominated by very, very young grains, around about less than 100 million years, compared to India, which apart from a very, very small number of young grains, is dominated by old grains. So Asia and the Kohistan-Ladakh Island arc have the same signature in terms of zircon, uranium, lead, but it doesn't matter because in this model, they are both already conjoined, so we don't have to care whether it comes from the arc or Asia. The first time we see these young grains on the Indian plate demonstrates the docking of Asia plus the arc with India. But this logic only works to date India-Asia collision if the Kohistan-Ladakh Island arc was already conjoined to Asia. If it wasn't, then because the Kohistan-Ladakh Island arc and the Asian continent share this same zircon signature, it could be just that the arc material has eroded and has collided and eroded with India, with Asia colliding with India plus arc later. So what actually is the evidence that the Kohistan-Ladakh Island arc hits Asia first? It's been long, long entrenched in the literature, so everyone has just taken it as such. But in fact, if you look at the evidence, it's not that strong. So for example, there's one piece of entrenched evidence based on, for example, the 95 million year cessation of subduction in the Karakoram. And in the past, people have said, well, that cessation of subduction must suggest that collision between Asia and the Kohistan-Ladakh Island arc had occurred. But actually, there are younger volcanics in the Kohistan-Ladakh Island arc. So Berg, for example, suggested, well, maybe this doesn't relate to Asia arc collision. Maybe it's just a reversal of subduction polarity, and the collision between the arc and Asia occurred later. So people began to question this mantra that the Asia and the Kohistan-Ladakh Island arc collided first. And in fact, if the Kohistan-Ladakh Island arc had collided with India first, then those young zircons might just be reflecting an arc-India collision. So as I said, this led to a second model where the Kohistan-Ladakh Island arc collides with India. And one piece of evidence here, for example, paper summarized Khan et al. We've got Kohistan-Ladakh Island arc volcanism ceased at 60 million years, when paleomag data puts the Kohistan-Ladakh Island arc very close to India, but far away from the paleomagnetic evidence suggesting where the southern margin of Asia was. Now, if this is the case, if the arc collided with India first, then all these previous criteria that we previously assigned to India-Asia collision actually might be explained by India-arc collision and the terminal collision between the arc and Asia, which reflects the final closure of the Tethys, might actually have occurred later. So in order to determine which of these two models is correct, if we're using the detrital approach, we must be able to differentiate between detritus from the arc and detritus from Asia. We need to find a time that Asian material, that is definitively Asian, landed on the Indian plate, not just arc material. So one way that we've discovered to do this is to use hafnium data from detrital zircons. Now here we have a graph of zircon, uranium, lead age on the x-axis and hafnium values on the right axis. And I've tried to color code these signatures of the various units of the Himalaya as best I can to the map up here. And you can see that we have very, very good high degree of overlap between the Kohistan-Ladakh Island arc in purple, and purple here, and the Gangdesi in orange, or Trans-Himalaya, which is the southern margin of Asia. So on this basis, it's quite difficult to tell the Kohistan-Ladakh Island arc apart from the southern margin of Asia. Yes, there are some older grains, but there is quite a high degree of overlap. However, if you go to these bluey-grey diamonds here, which represent the central Lhasa belt of Asia, here we see the central Lhasa magmatic belt of Asia, you can see that they have a negative these zircons have negative hafnium values compared, apart from a little, this is actually one Pluton here, broadly until about 50 or 75 million years ago, all the Kohistan-Ladakh Island arc is positive. In fact, until even younger, until about 50 million years ago. So if we find detrital zircons of this age with negative hafnium values, then we know they have come from Asia and not from the arc. So we did a study. This is the Kohistan-Ladakh Island arc, and we did a study on the suture zone sedimentary rocks over here in India in the Ladakh. This is the stratigraphy. We've got the Dibbling Formation, then we go up into the transitional series, the Kong Formation, and the Chulung La Formation. This is a sedimentary succession just south of the suture zone in the Tethyan Himalaya of the Indian plate. And we first of all dated these sediments using biostratigraphy, and we know they're about 54 million years old. Then we extracted the detrital zircons from them, and we looked to see if we had any evidence of Asian material in this sedimentary record on the Indian plate. Here we can see, first of all, looking at zircon uranium lead. Remember that India has, for the most part, an old signature, old zircons, apart from this small young bit, compared with the arc and the Trans-Himalaya Gangdesi of Asia, which have young. And you can see that our data from the Kong Formation and the Chulung La are totally, or pretty, not totally, but they're more or less totally young, which could be from the Kohistan-Ladakh Island arc or could be from Asia. So uranium-lead ages by themselves can't tell the difference. These smattering of old ages could be from India or they could be from the Lhasa block in Asia. So they're not diagnostic. So with this young data, young zircons, we know that India collided with the arc plus or minus Asia by 54 million years, which is the sedimentary age of these units. But the critical thing is, was Asia attached? So for this, as I showed, we have to go and look at the hafnium data. So now I've superimposed our data from the Kong and the Chulung La formations over our potential sources. And you can see, as expected, that a large proportion of the data represents detritus from either the Kohistan-Ladakh Island arc in purple or the Gangdesi Trans-Himalaya of Asia in orange, because these are very proximal to our sedimentary record. However, you can see we have got this smattering of grains which cannot have come from the Kohistan-Ladakh Island arc because they do not overlap with these purple values which represent the arc. Instead, they have very, very good agreement in terms of these two areas with the central Lhasa magmatic belt, which are these grey-blue diamonds, and the Karakoram, which is these grey-blue squares, which is over here. And these are definitively Asia. However, there are, as you might notice a small proportion of Indian plate zircons that also share this signature. We don't think they're from there based on 3 lines of evidence. First of all, these are very, very restricted in extent. It's just one formation. Secondly, they're only plot in this region, not plotting in this region as well, whereas our data, the red dots, clearly follow the double proportion of the central Lhasa magmatic belt. And thirdly, they have different hafnium characteristics. If you look at the 176, 177 hafnium versus the 176 lutetium, 177 hafnium, here we've got the Karakoram in blue diamonds. We also have some inherited grains from the North Karakoram, which are from the Asian plate, inherited into the Kohistan-Ladakh Island arc. You can see the Indian grains plot in a cloud that comes right down to here. And for the most part, our zircons from the Kong and Chulung La formation do not overlap with data from the Indian plate. So we think we can rule that out. So if we accept that the Mesozoic grains with negative epsilon hafnium that we found in the Chulung La and Kong formation are distinctive of the Asian plate, then India-Asia collision must have occurred by 54 million years. Not just the arc collision, but Asia and India. But it is only a few grains. I'm not arrogant enough to think that just my work is the only thing that could be right. What can we do to bolster this? Because our data are at variance with a lot of excellent work that thinks otherwise, and I don't just think that I'm right. So is it possible to go further east where there isn't that Kohistan-Ladakh Island arc? If we look in the suture zone or Tethyan Himalaya further east, then we don't have to worry about the arc. So here people have found Asian detritus on the Indian plate at 59 million years. This is the work of Hu et al., 2015. But that doesn't really help us much because others propose there's remnants of an intraoceanic arc that extends far to the east, for example, Aitchison et al. So we've got the same problem over there. I don't have time to go through and run through a summary of everyone else's data using different approaches that some consider evidence of an early collision and some people consider earlier of a late collision. What I will just briefly dwell on is the major unresolved discrepancy with paleomagnetic data. Now, paleomagnetic data put India far south of Asia at the time about 60 million years. Here we've got India at about 15 degrees south, and we've got Asia far to the north. So if we have collision, an early collision at 60 million years, how are we going to explain that India is far south of Asia at this time? So one model that could explain it is that we must have had in the past a much greater continental India that extended in order to have that collision at 60 million years, in order for it to have it be hitting Asia at that time. But that is an awful lot of continental Greater India to have to explain. Another model that we talked about was that actually the evidence for collision is relating to the Kohistan-Ladakh Island arc and its extension to the east, hitting India at this time. And it's not India-Asia collision. Now, this is the model that my data has problems with, and that we think we have data from the actual Asian plate onto India at this time. Another model is that the collision is between a microcontinent of the Tethyan Himalaya and Asia at this time, and there's another oceanic basin between the Tethyan Himalaya and India, which later closed. Now, a lot of people don't like this because they say there's no evidence of a suture between the Tethya Himalaya and the Greater Himalaya. When we talk about the detrital approach, one issue with that, so this is the model of Van Hinsbergen et al., is that he's noticed that there's problems that we have evidence similar to what I already showed you of Asian material in the fallen basin, so south of the Tethyan Himalaya, in the fallen basin, at about 60 million years. This is the work of Ding et al. And other workers. So how could that material have crossed from Lhasa through this purported Tethyan basin and onto the Indian plate? Well, that is an outstanding problem with this model. And Van Hinsbergen suggested, well, maybe the material that we see, the detrital material of zircon uranium with young ages, didn't come from Asia, or this block, at least not from the Lhasa block. Maybe it came from Afghanistan and the Afghan block. Now, the problem with testing this is that it's been very, very difficult to get modern isotopic work done in Afghanistan on the detrital approach or on any approach due to the current access issues that many people have there. So we are very excited to say that we have finally managed to get 3 modern river samples which drain the Afghan block, modern sand samples, from Afghanistan. And now we are going to characterize these samples to determine what the Afghan block looks like and then to test this model. Sample collection was done by our Afghan colleague, and I would just like to show you his efforts in a little video I have here. I was with him on WhatsApp, and I thought this was an amazing example of the collaboration that we can have. He was showing me what he was doing on WhatsApp and collecting the sample whilst I remained in the UK. So this is a quick video. So that was Daulat on his way to collecting the samples which drain the rivers of the Afghan bloc. We are now going to throw everything we've got at it, different types of analyses. Now this is obviously the important one, zircon, uranium, lead with hafnium, to test our previous models, but because these samples are so rare and so scarce, we're also going to throw everything else we've got at it, rutile, titanite, uranium, lead, strontium, neodymium, and mud, zircon, fission track, and apatite fission track, and petrography, to really get an idea of the first idea of what this Afghan block looks like isotopically. And then we will be able to test that model. So for me, my interim conclusion as to when India hit Asia is that for me, the jury's out. I think there is a lot of good evidence in both directions. So with that, I would like to thank you for, I've got one more slide, sorry. I briefly say, although I like the detrital record, it does have its limitations. For example, we do have to remember that it doesn't really work very well if you don't have the depositional age of the sedimentary record that you're looking at. There are issues of recycling of minerals, in that if you have a zircon that's come from its previous source, but has been deposited on a different terrain in a sedimentary rock and then eroded, you might not be thinking about its original source, you might be thinking about its redeposited terrain. We also have the issue of some minerals that don't last recycling, and so you've got weathering and diagenesis that might remove your minerals that you want. We've also got resetting of mineral ages. Once they're buried, they can go back above their isotopic closure temperature, and then the age that you get does not reflect the source region as erosion. It reflects the time of burial, so it might not be diagnostic of your source region. And that provenance studies rely on distinguishing between different tectonic units, so your tectonics units need to have different characteristics in the first place. So with that, I really am going to stop, and thank you for your time. I'm going to try to stop sharing screen at this point if I can. Well, I'm not sure I
Thank you,
can.
ma'am, for sharing your valuable insights and perspectives with us. Ladies and gentlemen, as we have Dr. Fraser and Professor Najman both active online in this session, the audience may go on with their questions.
So, hello, am I audible? I have a question actually with Professor Fraser, if he is available there. Is available, Professor Fraser?
Yes, I'm here.
Yeah, yeah,
Go
yeah.
ahead.
Sir, it is not actually a question. I want to hear from you, from your vast expertise, that you have shown in one of your slides that this evolution of this magmatic evolution from the Western Australia to the Eastern Australia, and you have shown through the Sumerian neodymium, or I can tell the neodymium isotopic model, that is your model age from Western to Eastern, it is evolving. So my question is with that this neodymium model age evolution, obviously your mantle metasomatism must be there from west to east. That is from the older to the younger part of your this Australian plates, and you have shown that number of plate boundaries were there based on this your neodymium model. So is there any evidence of increasing rare earth element or incompatible element, or the more the newer mineralization towards the eastern part than the western part of your Australian continent? That is my question. So if there any evolution in terms of metallogeny or mineral evolution as part with your this neodymium model age, as we know that neodymium model here may give you the mental metasomatism if we have gone from the western to the eastern part. So that's my asking you for that, because there is this much of evidence are there in India also, that number of suture zones are here where we are getting the neodymium model age across the suture zones, and from different parts it is evolving, and we are getting mineral assemblages which are really very, very this Audi mineralizations or these incompatible mineralizations are there. So is there any relation between these, and you have found it from the Australia, from your western part to eastern part? That's
Yeah, good question. And to be honest, I don't know the answer. I would say, though, that we do have some examples of rare earth mineralization in various parts of the country. So I suspect it's not as, I wouldn't expect it to be such a simple west to east progression in terms of enrichment in rare earths, because I mean, we're talking about several billion years worth of evolution here, from Yilgarn and Pilbara cratons through to the accreted Eastern Australian terrains, with, as you said, several or multiple episodes of subduction and tectonism at different times and different places. So I think the distribution of mantle metasomatism is going to be considerably more complex than that simple west to east progression. But I think it's an interesting question. And it does remind me that we have had some people here doing some, I guess, trying hard to try and map out the extent of mantle metasomatism via a variety of methods, trying to link up geophysical methods and geochemical methods. that's kind of an experimental thing. So really, I'm rambling now. Essentially, it's a very good question, and I don't have a very straight answer for it, except to say that we have rare earth mineralization both in the west and in the east, and in between, but they're different styles and very different ages.
Thank you, sir. Thank you. Thank you. I will talk to you later with this. Thank you.
Any other question from the audience is invited?
Just a second.
Hello. Actually, my question is to Yanni. So often I'm asking about the MDA. It's not related to the Himalayan topic you are dealing with. So people often refer MDA as the age of deposition, but the depositional age could be much younger than the MDA, even millions of years, right? So in that case, if there is a depositional hiatus for over a millions of years, and my MDA is only giving a older age, how to handle it with the depositional age? Thank you.
Yes. So that is a limitation of the detrital approach. Indeed, maximum depositional ages will only give you a maximum age when you're using, for example, zircon, uranium, lead. You can try and use chronometers that have lower closure temperatures that will be closer to the depositional age, but don't go too low in terms of closure temperature, because then you'll have the problem of resetting. This works much better in the Himalayan system where you've got rapid exhumation. So I, for example, will often use mica argon in the Himalayan Fallen Basin because mica muscovite is very prevalent in the high Himalayas, the greater Himalayas. The greater Himalayas have been subject to rapid exhumation. Therefore, it's likely that your lag time is what we call it between the mineral age and the depositional age will be short, because it means the mineral, so for the example of muscovite, has crossed through its closure temperature in the source region around about 350 degrees. You've then got rapid exhumation through those final kilometers in the source before it lands in the basin. So when you've got rapid exhumation, it's a short lag time. But in a system where you do not have rapid exhumation, then using maximum depositional ages is really not a very helpful approach. What can you do then? Well, if you're lucky, if you're in a marine system, you can use biostratigraphy. If you're in a continental system, if it's not too deformed, you might use magnetostratigraphy. That's a lot of work. You've got to get people drilling a whole sedimentary succession. And then if you're lucky, you can find some ash layers to tie it to. But if there aren't any ash layers, you're going to have to try and tie it to, for example, long normals, but you've got differences in sedimentation rate. So it is tricky. Thankfully, I mostly work in the Himalayas where I've got a short lag time, so I don't have so much of a problem. But those of you in more cratonic settings, yeah, you might have to go for some magstrat or something. So as I said, it's a limitation of the approach. But
Yeah.
thank you very much for your question.
Yeah, thank you very much. Actually, I was looking for a cratonic part of India, which are mostly deposited around 2.7 billion years. Then the deposition started, possibly we don't know after how much time. But people are referring the MDA to the last detrital zircon of the cratonic part, which is possibly wrong. So that's why I was confused. Thank you. Thank you for your answer.
Yeah, it's difficult.
Any other question from the audience?
I might just jump in and make a comment that we have a similar experience here in Australia. We quite often have people tempted to start using MDA zircon ages as if they are depositional ages, and yeah, we often have to remind people, no, it's not a depositional age at all until you've got some independent evidence to corroborate that.
Yeah, thank you. Actually, my question is from Mr. Karanja. He's there, I think. Okay.
No, sir, he is not there.
Okay, then I can contact directly.
Okay. Thank you so much, Dr. Fraser and Professor Najman, for giving your valuable time to us. I thank you so much once again.
Thank you. It's been a pleasure.
Yeah, thank you. My thanks to you as well. It's been great to
With this, we will now take a break for lunch, which has been arranged in the convention hall at ground floor. I request everyone here to kindly reassemble in this hall at 14:30 hours so that we can continue with the afternoon sessions and more engaging presentations. Please also note that similar technical sessions will be conducted in the main auditorium, mini auditorium 2, and the conference hall, which each featuring different themes and presenters. Interested participants are welcome to attend those sessions as well. Thank you.
Professor M.K. Panigrahi.
Okay.
So,
Sir, I think, yes, sir, this will.
so I'll be using this with my pen drive.
Yes, sir, you'll be using this laptop here only.
Okay, okay,
And sir, I'll just call someone to arrange this thing for you.
okay, fine.
Are you still there, Yanni? Can you hear me?
Yeah, I think he's saying something.
Hello?
Yes, sir. Sir, we are closing this session for lunch now. Yes, sir.
No problem. Okay, I'll sign off now. Thank you very much.
Thank you,
See
sir.
you.
Thank you so much.
See, this is in the office 21, and generally from
Welcome back, ladies and gentlemen. We now commence the first technical session of the day, which opens with a distinguished keynote address by Professor M.K. Panigrahi on state-of-the-art knowledge on orgenesis and new directions of research in Indian context for exploration implications. This session primarily focuses on critical advancements in oogenesis, mineral exploration strategies, and resource assessment challenges, an area of immense national and scientific importance. To guide this session, we are honored to have with us Sri Aya Kirmani, former Additional Director General and Head of the Western Region, GSI, and Sri M.N. Praveen, Deputy Director General and Regional Mission Head to Southern Region, GSI, as our esteemed chairs. Sri Kirmani sir is a distinguished geologist known for his expertise in metamorphism and mineral exploration. Even after retirement, he remains actively engaged in the geoscience community. His research publications continue to be widely referenced, reflecting his lasting impact on the field. Our co-chair, Sri M.N. Praveen sir, is a distinguished exploration geologist leading investigations for a wide range of mineral resources, along with numerous national and international publications. I now respectfully invite Sri I.R. Kirmani and Sri M.N. Praveen to kindly join us on the stage and preside over this session. I also request Sri Mohammad Naushad, Superintending Geologist, Central Headquarters GSI, as a rapporteur to record the proceedings of this session. So kindly come up to the stage. This is technical session.
ओके कहाँ चला गया ओके राजस्थान पीपीटी उसमें है मेटालिक ये है वो नंबर 6 है ठीक है तो ठीक है टाइम है एक बार ओपन करके दिखाने दीजिए सबसे लास्ट स्लाइड दिखा दीजिए वही होगा ठीक है ओके फाइन छः ही है ना सेशन में
To open this session, we have here with us Professor M.K. Panigrahi from IIT Kharagpur. a distinguished expert in ore geology and geochemistry with recognized specialization in fluid inclusion research. Since joining IIT Kharagpur in 1995, he has made significant contributions in understanding hydrothermal ore deposit formation in India, covering minerals such as copper, molybdenum, tin, and gold. Professor Panigrahi has published 75 research papers, authored several book chapters and conference proceedings, and guided 23 doctoral students across diverse fields. Today, Professor Panigrahi will be sharing his insights on the state-of-the-art knowledge on ore genesis and new directions of research in the Indian context for exploration implications. And so, with great honor, I now invite our esteemed speaker, Professor M.K. Panigrahi, on the stage to kindly begin his talk.
Am I audible? I think the screen is not coming at the. Okay, a very good afternoon to all of you here. First, hearty congratulations to Geological Survey of India on completing 175 glorious years. And let's hope that by the time it's the bicentenary year, things should be much, much better. We can have some breakthroughs as we all are wishing to. And apologies also because this talk is not going to be technically very engaging. I'm just going to share my thoughts and some of my insights. And my talk will be something like, the old V. Santaram type movie. If you are looking forward to having some Bahubali 2, 3 or RRR, then it will not be fitting to that quite comfortably. But I guarantee you that it will definitely have some thing. Okay, so I have been doing ore genesis for mostly last 38 years. And I have always been wondering that actually what I am doing and whether what I am doing is actually having any societal benefit or whether I'm doing anything worth rather than just telling stories. So we were basically trained or basically initiated that we were studying the ore deposits to give insights to people who are doing the exploration so that they should be able to discover new deposits, develop some new methodologies for exploration based on what you tell them as to what the ore deposits going to tell about themselves. So sometimes it comes to my mind whether this is ore genesis in mineral exploration, whether it's a myth or reality. Many of the things I will throw the questions to many of the young people here. I don't know how many really young GSI workers or students from different places. Or I could have made the talk as a title like Reflections on a Tortuous Journey Through the Ore Genesis Research, because it has been tortuous because, if you look back, many of the things have changed, ideas keep changing, new ideas come up, and sometimes you feel that, you are confused that what you knew or what is coming up, how much it's helpful, how much of science is getting in, because that's what sometimes I feel, the same as that of thermodynamics. You study thermodynamics, first time you think you know a lot. You read thermodynamics, so the second time you think that, I know a little bit. So after a number of times when you read thermodynamics, you lastly conclude that I know nothing. So that is exactly my state that, okay, now I said, do I know ore genesis? Okay, so the thing is that every journal coming out, every number, scores of papers coming, many new ideas, and if someone right this point of time someone wants to investigate the genetic aspects of any mineralization, hydrothermal mineralization specifically, because they're the difficult ones, because they involve fluid. Fluid can be from any source, and a whole lot of complications get in. So the literature now is dauntingly vast, and you'll have flooding of ideas in a world of competitive publishing. Once feel like you were like a Rath Yatra. So you have no much of freedom to move yourself. You are actually moved by by the crowd. So many new ideas, many things are just getting in the middle of a stampede, and then you have to have your own thought process strong. And so here, my suggestion to the youngsters is that develop to make many open queries. What ideas are going on for decades, how they have actually helped us in solving many of the mysteries. But then, until and unless you raise open inquiries, science will not progress at all. So, you must make open queries rather than being blind followers of the so-called authorities. I will just justify this through my own experience of working on the two important mineralization areas in the country. One is the enigmatic Malanskan copper molybdenum gold deposit, and the other one is the auriferous schist belts. So when this request was made to me about this conference and to say something about it, it just got into my mind that, well, are we always, because I have been teaching the subject of mineral exploration more than I have taught orogenesis, that can we say how much of why we are not that endowed with metals like compared to countries like US or Australia or Canada. So then the question is that whether it is because that we have not explored ourselves enough, or they are just not there. So the idea that comes into your mind, unless you go out of the box approach and you think that no, there must be something coming new. So for example, any metal endowment in any particular country is a function of the geological diversity. So when you look at the Indian shield, I don't go to the extra-peninsular because Himalayas will always remain very enigmatic, and I don't know whether we'll be able to really sort through the Himalayas to discover many deposits. That will be really challenging. But if you take the Indian shield, then its geological diversity is not as high as compared to what is the Chinese continent, like their South China, their middle of the Inner Mongolia, and we definitely don't have that. So now, is it time for us to press the panic button, or do it at a war footing, or we say Dilli dur hai? And another thing is that if it is not there, we cannot discover it. That's very simple. Like for example, many of you, I don't know how many of you would have heard the name of Richard Silito. He used to be he's the kind of the god of porphyry copper deposits, who worked all his life on the Andean deposits, porphyry copper deposits in the Chilean Andes. And so he was once invited by the government of South Korea that please come and explore for porphyry copper deposits in our country. And it's anybody's guess, because if it's not there, it's not there. Anybody comes to look for it, will not get it. Okay. So that's a real difficult question to answer. And the buzzword of today is, of course, we have already heard, this critical metals. Like what Kat Goodenough said, that everywhere they say critical minerals, but I stick to my word of critical metals. And thing is that we all know that the material, the stuff that we are looking for are the exhaustible, non-renewable mineral resources. And until and unless, so in addition to building up newer strategies, technologies, like the buzzword of today is artificial intelligence and so on, we also should think of a situation like, what is written in this red, I don't know how many people know here, way back about 40, 50 years back, Brian Skinner, one of the very renowned economic geologists of the world, who was once the editor-in-chief of economic geology, he had an article in Scientific American. I would always suggest, when I go to class, I tell people, read that article, that's very interesting. Is there a second iron age ahead? Because iron is a abundant metal compared to You talk about the base metals, talk about the coinage metals, precious metals, they are all scarce metals. So their distribution pattern always follows a different kind than that of what you see in case of this abundant metals like iron or aluminum. So will there a time come so that many of the metals will be replaced for in any kind of our technology? So then we should be also look into that aspect, that we could always think, like for example, you talk of the heavy rare earth magnets, rare earth magnets. So other than dysprosium or terbium, is there any other way to, any other element that could substitute and can give the similar magnetic properties? Right there, this moment the technology possibly say that no, not much. But we could always think of something, the technology which is going to be the technology of the future. Anyway, that's of course not my cup of tea. Well, so this is a little prophetic, because whenever I begin or I give a talk on overgenesis, I always refer to the person who initiated me to this field, and I just read out the prophetic words. There is always a criticism amongst the practicing mining geologists that people like us, we always go there and make very nice explanations about how the ore deposit formed and when it formed, making all sorts of nice explanations, but only after it is discovered. And believe me, that mineral deposit occurrence has got a very substantial chance factor in it. We say that we're exploring. And so the discoveries are made. Definitely there are efforts like what I will be discussing about, but there is always a significant chance factor in exploration or discovery of any particular mineral deposit. So it's more than 6 decades now that how long we will have to continue such criticism. Means we ore geneticists have not really helped much in discovering new deposits, but we have been talking big about how this deposit is formed. We can go on to any sort of like sophisticated analytical data and talk something. So but one thing has to be admitted, that orogenesis and mineral exploration have gone hand in hand, in the sense that after discoveries are made, then the literature on ore deposits have been getting enlarged and getting more and more and more, and we know more about, but then only after they're discovered. So if we say that what was told in 1997 by Brian Skinner, you could read them out, that what we don't know about the ore deposits at the system. The source of metal, source of fluid, the magnitude of the mineralizing system, constraints of space and time, and the source of metal and sulfur. So it's kind of gives you a checklist of what you must generate to understand the deposit. So that's what I have to put this something like a microscope to microxens. XENS is essentially the X-ray absorption near-edge spectroscopy, which is a very sophisticated, I mean, it is just not to sound the name of one sophisticated equipment, just to tell you that it has been going on and on and on, that okay, one microscope was not enough, go to a microprobe, it's not enough, you go to an LAICPMS, it's not enough, go to mass spectrometer, do sulfur isotope, it's not again enough, and then go on and on, and then any kind of a sophisticated high-end equipment is there that you're going and generating some data, and you say something. So once you have generated some data, you of course you have to say something about how the deposit is generated. But then how much of that knowledge will actually be translated to be helpful for us to explore for any building up of the exploration strategy is something to be really think about. And well, so finally it will all be artificial. So we will to ask ourselves whether is it going to be all artificial intelligence. I will just make my comment before I conclude. Okay, so when it comes to the exploration of mineral deposits, I always refer to, even though the paper is quite old, 1994, the paper of Woodall, where the discovery history of Olympic Dam deposit is given. Usually one has to wonder, started with a concept of Proterozoic rock, then what should be the exploration strategy? Then came the concept of leaching of basalts, metals like copper, and then getting enriched in from the sediments. And then came the intersecting lineaments, geophysics, photogeology, So if in the audience people, any one of you have not gone through it, I'm sure if you go through it, you will find it very interesting. So now, the title of the paper was Conceptualism versus Empiricism. Which one is actually more helpful? And you will definitely conclude at the end of it that yes, the end of it says that in the field of observation, chance favors only the prepared mind. And one has to be remain prepared, have to be open enough to change his ideas, to adapt to, like say for example, starting from basalt leaching to lineament intersection and photogeology, geomagnetic anomaly, then geochemical mapping, and finally put a drill hole there. And even when the first drill hole was there, the drill core was something like a material, blackish material. They thought again it should be basalt. But then when it gave a lot of copper, the concept of the metal getting leached from basalt then failed. Because if the basalt was leached, then how the copper concentration would be so high. And then you can see the story of it. And after that, about 7 or 8 drill holes failed, and finally the Olympic Dam deposit was discovered. So then, what was the repercussion of the Olympic Dam discovery? That it was definitely a major breakthrough in mineral exploration in the whole world. And my Australian colleagues very jokingly tell, is the right deposit discovered through all wrong models. And so that's what Woodall quoted Pasteur. In the field of observation, chance favors only the prepared mind. So now, these are some of the things which my own criticism, because I was following this literature from that, because Olympic Dam deposit was discovered in 1975. At that time, I didn't start to study geology. But after that, when I saw this, once upon a time, I was very much digging through all literature is happening in mineral resources all over the world. So you could see here, this is a publication from USGS that came in 1992, mid-continent of the United States, permissive terrain for Olympic Dam deposit. So because Olympic Dam deposit was such a major breakthrough in the history of mineral exploration in the world, giving you the richest uranium, copper and gold deposit in one place. So the Americans, I mean, I'm not making any critical, not criticizing anybody, but the Americans started to immediately explore for such deposits in continental interiors in North America, US and Canada. So, did they get any? Answer you could find. They may not get any, they would not have got many, but what they did is they reclassified many of the existing deposits in North America as IOCG. And then this deposit name called IOCG, iron oxide copper gold, it actually was coined after the discovery of the Olympic Dam deposit. And I say that it's kind of an IOCG wave that passed through and still passing. Any deposit is now being put under the big umbrella. IOCG, okay, Olympic Dam deposit didn't have any iron sulfide, so let it be ISCG, iron sulfide copper gold. If not, okay, iron oxide apatite, and then iron oxide alkali calcic alteration type. And that would, and pre-orogenic, synorogenic, post-orogenic, anorogenic, everything could come within that. My point is that if we build up such models, they will not be helpful at all for us to build any kind of a concept of mineral system. So, but the way it's going, barely any deposit will survive reclassification other than IOCG. I mean, it's a constructive criticism, not that you don't call it. It's kind of every deposit has its own distinctiveness, own uniqueness. So we have to reveal that. And then we see that like if, for example, the deposit on which I worked for a long time, the Smalanskon copper deposit, which I'll be covering a little bit. Okay. And I don't want to, because it might become a lengthy Olympic Dam deposit characteristics. Most of you know that how it is. And especially the fluid mixing model. Initially, they were not, the initial fluid mixing model was never involving any magmatic fluid. Low temperature fluid, one oxidized, one reduced. And since it's a uranium system also, all we know that copper and uranium cannot come from the same source rock. So the source rock have to be different. The geometry of the Olympic Dam deposit. In fact, I can say I have not seen any other deposit which actually mimics the Olympic Dam deposit. Maybe some of the satellite deposits in the Gawler Craton, where you all know that the southeastern Australia in the Roxby Downs granite, there are some other like Oak Dam and other kind of deposits which are later on discovered, which are having some similarity. It's very likely, but in other parts of the world. Well, so that was the kind of IOCG wave. So I'll now come a little bit, change my topic to the new paradigm that is there in literature that's called the mineral system paradigm. Many people will think that possibly Wyborn 1994, even I found out recently that it is actually the great Bill Fife, Western Ontario, Canada. He was the one to talk about mineral systems for the first time in 1976. So and then Leslie Wyborn, they thought that, okay, it will be comparable to petroleum system. Petroleum system has got source, pathway, trap, but we all know that mineral systems can never be compared as such with the petroleum system, because the concept of preservation doesn't much apply to the petroleum basins. We don't really much talk about how much of petroleum has been actually weathered out or gone out or lost after the trap formed. I don't know. I mean, that's my understanding. So this is what was the paradigm of mineral exploration, building up a mineral system. And we know that the mineral system is far more complicated because one of the many reasons that there are non-uniqueness. Many things can, a source of metals could be multiple, source of fluid could be multiple, and multiple processes can also give rise to almost identical things, which we know from standard orogenesis literature. So the concept is, okay, if we could, so this is what, so the mineral system means is essentially that whatever we learn about orogenesis, we would like to translate it to exploration targeting system. And but there is considerable haze, uncertainties over the implementation scheme, in spite of, so almost like you will see that scores of paper every time you will open up journal or geology reviews or journal of geochemical exploration or all other related journals in the field, you will be flooded with papers now talking about mineral system approach. And almost everybody will say, okay, it's as if it's very definitive. But then you know that there is hardly any equivocality that could be there. And it's really difficult to translate a mineral system to a targeting system. That is followed by one paper by Stephen Hajming, who said that, okay, a mineral system cover this. So no strong, so what happens then there is that this mineral system approach is supposed to give us the knowledge-driven part of our prospectivity modeling. I think in Geological Survey of India, people are very familiar with this terminological prospectivity modeling, which is knowledge-driven and data-driven. So the knowledge-driven is supposedly come from the understanding of our orogenesis, which is now essentially going in the form of mineral systems. So this, yes please? Hello? Yeah. So non-uniqueness, many mineral systems may have similar lithospheric architecture. And one of the most important thing with mineral system approach is that you could see this diagram is from McQuaig et al. So you will not get a good correlation between the hierarchy of this critical process, constituent process, deposit scale process, and like from this diagram that you could see that in the larger dimension, when you were thinking in terms of lithospheric structure, tectonic lithospheric, the architecture of the lithosphere, there you were in a stage where it is essentially a prediction kind of a stage, and then prediction to detection. So it gradually, when you zoom in, come to the deposits and look at the deposit scale processes, which tells you about the hierarchy. So this hierarchy is not very much reflected from the diagram which is there on the left side. You could see that when source is a much more regional or even crustal, whereas pathways could be narrower, even physical throttle is still narrower. And then each of these processes, like the critical process, constituent process, they say that it operates on a hierarchical manner in the sense, and a probabilistic manner, that if your probability of a critical process is 0, then the probability of finding the deposit is actually 0. So you have to have first some positive probability value for the critical process, and then when you're going down, then gradually you will land up with a probability which will be more than 0. Okay, so for example, you say source, if you say consider source, consider a regional scale and have a critical geodynamic setting as the mappable targeting criteria, a proxy you think could be geochronology, but geochronology will always will be one of the most critical things to really interpret. Many dates, many edges will come up. Today there is, like I'll give you an example from Malanskan. Contraction erosion, fold belts, maybe the targeting criteria, the proxy is geophysics. Geophysics in most of the cases is indirect, inversions, all you know. Okay, so how much time do I have? 2 minutes more, I think. Oh my goodness. So this is Malanskan deposit on which I landed up some 38 years back. And you all know this is the big pit. And when I landed up there, so this is the mode of occurrence of the deposit. This map, mine scale map, is actually maybe 20-25 years old, but that shows the yellow one is the major quartz reef, which is the main ore body. And you see that in all its geometry, it occupies a major fracture zone within the granitic country, and these all maps possibly are at least 20-30 years old, but means they're not obsolete, they're still valid. And situation like this mine scale map at different levels. And situations like that, you have the pink granite in which you have variable extent of enrichment with respect to the pink potash feldspar within the mine pit, and then what originates story we are going to tell about that. Go and date the rock, do RBSR dates, okay, they may be erroneous. Go to uranium lead Concordia, you will say that okay, that's very acceptable. But then someone comes up with saying, oh, we dated uranium osmium dating. Okay, then, okay, so that date is supposed to be challenged. No, uranium osmium dating, something is different from the uranium lead Concordia dating. Then comes the latest, okay, somebody say lutetium hafnium, again going up to 3.25 giga age. So you see that it is actually not the age dating methods going to solve your problem. And this is what kind of a model that I built up, taking many of the methodologies like ore petrography, mineral analysis, bulk geochemistry, RBSR dating, shrimp uranium lead zircon dating, fluid inclusions, thermodynamic modeling of mineral fluid interaction, sulfur isotopes, magnetic susceptibility, modeling of the metallogenic potential. It looks like as if it's not adequate. Still, I mean, there is a lot more to go. What else you should do? Sky is the limit. And sometimes I say that, okay, if this is the quartz reef of 2 kilometer long, this much of width, so one should try to model that how the quartz reef would have formed, then fall back on some kind of chemical modeling, diffusive process that could have formed, and you find out, okay, this could take some of the years as 5 to 8 million years time for this reef to form, and that might produce some constant. And then you think, am I going to build up some kind of a model of exploration for this deposit? Because of lack of time, I'm not able to discuss much. There are comparable granitic country like the Dongargarh granite, there is Bundelkhand granite, where there are quartz reefs, also even much larger dimension. So what idea you are going to extrapolate from this to the other unknown areas? Okay, so I'll have to skip this. Now, if you say that it's a porphyry type deposit, then how a porphyry model misled exploration at Malanskan in the past? Someone said that, well, this is a porphyry type deposit. Porphyry type deposit does never occur alone. So there will be many other deposits. So call the people to do vertical seismic profiling. And I can never think of in all my imagination that how a vertical seismic profiling will be able to detect sulfide ore body. And then someone told them that, well, this reef, mineralized quartz reef that you are seeing 2 kilometer long with an average width of 70 meters is essentially an enriched part of a enriched blanket in porphyry copper deposit, and that is actually faulted. One side of the fault is now, that is the mine. There should be another limb of the fault. Go and drill. You could always imagine what could have been the result. So a porphyry model will take you nowhere to formulating an exploration criteria in deposit like this. So this was a thing like in which my idea was that there was another phase of leucogranite which had some indications of providing the metal and the sulfur for the main mineralization zone, and I dated this granite, this leucogranite, which RBS had date was something intermediate between the edges that I got for the mineralized granite and the regional granite. And somehow the story I tried to build up is that this leucogranite phase must have been instrumental in bringing about mineralization at Malanchkar. Okay, so I of course have to. So now I said that what data possibly will help to solve this case: oxygen isotope, oxidation state of the magma, more precise age dating, in situ destructive analysis of fluid inclusions when the protocol itself is doubtful, in situ sulfur isotope makeup of sulfide minerals. Now it would be a never-ending wish list and may go on and remain inadequate even. So this is the experience. I'll just take 2 minutes to tell what is the problem here. This is the orogeny gold model, which came up in 1986 by David Groves, the popular metamorphogenic model of mineralization, where you could see that fluids that are generated during at the high pressure temperature metamorphism of the metasedimentary piles with some synkinematic granitoid, and the fluids to be channelized through the major fault zones and can encounter a mafic body, can encounter BIF, can encounter a carbonaceous sediment, and can give gold deposition in different locales. And that model was quite a popular one, apparently explaining the diverse locales of mineralization. But then during some time it came that okay, this is possible through bringing in seismicity. That means the fluid that is actually accumulating here or is remaining in a which is called as supralithostatic pressure, building up a pressure. That fluid periodically gets released. This fault just acting like a valve. That's called a fault valve mechanism, which was very popularly known as the Simpson cycle. But nobody tried to the question. Now the option is that you may say that okay, do all your stuff, do all sorts of modeling, do boron isotope in tourmaline, and say that okay, the fluid is metamorphic and the process is Simpson cycle. But if you want to raise some open queries, they always get into try to understand how this earthquake geology will get in, whether how the geology of the crust was in the late Archean and early Proterozoic time, and the seismicity that is observed in the present day, how much of it could be extrapolated to understand there in that time. Then get into a lot of things like porosity permeability, go to the fault anatomy, and when we try to do some modeling on this, we observe that the process of seismic pumping and buildup of supralithostatic pressure and periodic release of fluid is actually not quite tenable or not quite explainable, whether these high angle reverse fault acting as valves. So I am not able to get into the details of the numerical modeling part.
Professor Panigiri, will you please sum up? Because
yes. So just look at this. So we talk of mineral systems, we talk of many of these strategies, and here are the Chinese. About 40 years back, they started something called the Regional Geochemical Mapping Program, and in that Regional Geochemical Mapping Program, the geochemical, the blocks, the regional anomaly, local anomaly, all these things came, and they say that they have discovered about 1900 deposits, and that's their story. But then we have been doing it for at least last 20 years, and we have to ask ourselves how much we have been able to progress. Although I use the National Geochemical Mapping Program data quite extensively. This is an example by using a multifractal model to separate anomalous zones from background, and they come out to be very handy. Okay, so this I'm not because of the lack of time. This is something something of whenever we are trying to do exploration, the challenge is to reduce the search space. So how can you reduce the search space? So you use all sorts of algorithms. So these are coming up very easy because software platforms are available. Anybody can do it. do it a weight of evidence, do it for logistic regression or whatever kind of models you think of, and you were doing a reduction in the area, even something like your knowledge driven, data driven kind of model that you produce some mineral potential map. Okay. So just one more minute. The question is that when the mineral prospectivity models are proposed by either say academic like me or you or anybody, why the industry doesn't accept it? So industry doesn't accept it because industry thinks that it's a black box approach, and they don't understand the integrity of it, the nitty-gritty of it, the complexities of it. But then you give them a geophysical anomaly map, they will be happy to go with that and put a drill hole, even though they don't understand what's the geophysics in it. So existing, so they say that you only validate with the existing deposit, you don't show us the new deposits. So my answer is that you have to have the confidence that when I am giving you a map with this reduced search space, you should go and put a drill hole there and see whether I am right or wrong. And in mineral exploration, if 3 out of 10 drill holes are coming out to be successful, it's a huge success. Okay, so the future of mineral exploration will be MPM with all supercomputing tools will be there. Hybrid models will come, both data driven and knowledge driven. Geophysics will keep dominating. AI ML will come. But the question is, can we predict in some quantity? Many of the mineral prospectivity modeling are only just going to tell you here this is potential zone, here is potential or something, but nobody will tell you how much of tonnage of the ore you are going to get there. Okay, so I say that go, explore, discover, and tell why, where, and when the deposit form, and then in that case, economic geologists will no longer be called as endangered species, and in another 25 years down the line, when I come here, when you will be having your bicentenary meeting, if I am there to deliver a lecture, I'll be having some smile on my face that Origenists actually helped in bringing out. So I'm very sorry to have taken a lot of time. Now, any questions?
Thank you, Dr. Paniguri, for a very interesting, a few, 2-3 questions.
Yeah, I know, because I would love to discuss hours, yeah. I mean, see, that's a very interesting question. People are like, say for example, people like me or orthodox people like me, we always say that artificial intelligence can never replace human intelligence. So now they are saying that instead of AI, something called IA, intelligence accelerated. So AI, people are using it as a buzzword, but say for example, you are going, which component of AI you are using? You are using machine learning, classification technique, you use support vector machine, random forest, and all sorts of things, which people were actually doing standard statistical exercise long since. Discriminant analysis, linear discriminant functions, nonlinear discriminant functions, so they are just packaged. So those were used as statistical tools, they will continue to be used. Now there is one interesting thing, that industry doesn't accept your MPM, right? But the same industry guys will come to do a PhD in a university, they will also do the same thing. So what is happening now is that lots of digital image data are coming. So lots of digital image data, and they're doing extensive machine learning like random forest or a support vector machine to classify deposits, potential areas from barren areas. But there is one important thing that somebody has told, that your drill hole data will only come from prospects. Your drill hole data never comes from barren area. So if you are devising a classification algorithm to discriminate between the productive and the non-productive area, you don't have enough data to give on the non-productive areas. Suppose I want to do it in the Hatti-Muskie cyst belt. I will have the drill hole data almost just near around the Hatti mine or something. I will not get the extensive drill, who will go to drill there? And so that is why remote sensing with better techniques, even drones might come. Like, you have the hyperspectral imaging from drones that I could see as a thing coming up, maybe very useful. And then most of these people will definitely, so this has to build up gradually the confidence, and then I think we could hope that we could do something. And of course, geophysics is coming in a long way by doing the the lithosphere architecture imaging, they are now getting conductive, low resistive zones all below the entire, in the lithospheric, all 80 to 120 kilometers depth. So they are going to tell something different story, whether that is because of fluid or because of sulfide or because of graphite. Geophysics is indirect. If you get low resistivity zones, then that could be because of fluid, that could be because of sulfides, that could be because of graphite also. So they rather say that it is more likely due to graphite. If they are all graphite, then how do we build our mineral system? By saying that from where the metal has come. So, this discussion can go on for.
Okay, thank you, Dr. Pandey. Next question, if there's any.
Hi. Hello.
Yes?
Hello. This is from Shushovan from GSI.
Aha.
Sir, what I understood from your presentation, actually I am interested about Malanjkhand copper deposit.
Aha.
So you told the evolution from our textbook, Malanjkhand is a porphyry copper deposit, to that evolving idea about the Malanjkhand copper deposit. And if I am not wrong, Professor Nehru and Sikka first boldly told in 2002 that Malanjkhand could be anything than a porphyry copper deposit. Now, the present understanding you are telling about that, it could be derived from a granite, right? So the granite you are talking about, Malanjkhand granite?
Yes, the 1400 square kilometer area. But then, yes, so then this discussion, of course, would be lengthy because it might.
No, my question is, sir, actually, so
These questions can be addressed by email to Dr. Panigre.
if you are saying that Malanjkhand granite is the host or the source for the copper or the sulfide deposit over there, then why there is a single deposit in Malanjkhand?
No, that is the problem. That is not a single deposit.
Acha,
You get prospects in
Mr.
Garidogri,
Sushovan,
Gidori.
you can have a personal discussion with Professor
You have
Panigre,
prospects in
because it's time already.
Sitalpani, Gidori,
overrun.
Garidogri, they are all prospects. It is not single.
Sir, I have just a short question.
Yeah, you can have personal discussion with him. Okay.
Who?
Let us go next.
Sure.
Time is up. Thank you, Professor Panigre.
So you can keep it. Thank you, sir. Sir, thanks for the enlightening lecture. Sir, I would like you to stay with us on the stage as I now call Shri R. Bijay Kumar, Deputy Director General, Geological Survey of India, to come up and felicitate our esteemed speaker. Yes.
So all the very best to all the GSI people. I'm looking forward to a lot of things coming from GSI in the coming days. Okay, thanks again.
We will now proceed to our technical sessions. We have a total of 6 presentations. Before we begin, I respectfully ask all the presenters here to remain within their designated time limits to ensure the smooth flow of the program. I also request the audience to hold your questions until the end of the session. We will have a dedicated Q&A which will help us to stay on schedule. At this point, I would like to hand over the session to our chairs. Also, sir, I request you to kindly moderate the presentation timings as per the schedule provided. Thank you, sir.
Yeah, may I request Dr. Sanjay Devnath for his presentation.
Hello.
it is, here it is coming, but it is not coming there. Okay, now it has come. Okay. Okay, thank you. Good afternoon all. Myself Sanjay Devnath, senior geologist from Geological Survey of India. I was working in Rajasthan for last 12 years, 11 years roughly, and I did many mineral exploration projects over here. This is one of my mineral exploration projects I have carried out during 2022 and 23. So my topic of presentation is structurally controlled hydrothermal copper, molybdenum and associated gold mineralization within gneiss of Mangalore complex or Villavara supergroup. The area is Danta, Balavanta and Jatia area, which is situated in Ajmer district of Rajasthan. So now my work is entirely on the basis of field work and the field evidence of mineralization, and very basic things I have done and now which I am going to present in this platform. So let's talk about the few introduction about the area. So you all know Rajasthan has many interesting and distinct aspects, and geology is one of them. And we know that Rajasthan records the rock from Archean to recent. And also Rajasthan hosts a very, is a very mineral rich state in the nation in terms of availability and viability. And roughly 57 minerals is produced in Rajasthan state single-handedly. Now my present abstracts deals with mapping, mineral exploration of copper and molybdenum and some associated gold mineralization in that particular area. It is, I already told, is covered the Mangalore complex of Villavara supergroup and partly Ajamgarh formation of Delhi supergroup. Now, as I told that my work is entirely based on surface evidences of mineralization and exploration by collecting different types of surface rock samples. Generally, we collect during mineral exploration programs like bedrock sample, channel sample, such type of sampling I have carried out and I did the work. So this is a location shown in Booger gravity anomaly map, and if you see there is a geophysical axis in northeast southeast direction, and my block is shown in the rectangular block is shown here, and if you see in the northeast direction, there are a lot of deposits are there. Kaya deposits are there, Gugra deposits are there, and recently explored copper, gold, and molybdenum deposit done by GSI. The excellent work has been done in Ladera area, which is still exploration is going on. So this is in the south of that particular area, my area is situated, and that is another aeromagnetic anomaly map. In that aeromagnetic anomaly, I have also some anomalies situated in the particular block. Now, if we talk about this is the geological map. I have mapped 50 square kilometer area in the topo sheet number 45J/11. And this is the geological map, and you can see that in the southern part entirely covered by the BGC, and the northern part is entirely covered by the different litho units of Delhi supergroup rocks. Apart from that, these areas structurally deformed, different type of foliations, lineation, and folded structures has formed. Apart from that, a major ductile shear zone is passing through the area, and precisely it is between the contact of BGC and Delhi supergroup rocks. This is the extent of the shear zone which I have observed during my field work. Slide is not changing. Now, these are some field photographs, structural photographs, which I have encountered during my field work. So these are some structural photographs. As I told you, I have found during my field work some color banding in the calc-silicate schist rock, bedding in quartzite and tight isoclinal F1 fold within the quartz biotite schist rock, and other F2 folds found in different other types of rocks, some granulation cleavage and the F3 folds and S3 foliation planes. These are the structures we have encountered during my field work. And this is the ductile shear zone. This is the extent of ductile shear zone, and there are a lot of evidence of shear zones have been found during the field work also. These are the photographs of different shear sense indicators or shear zone features First one is it is a SC fabric which has been found in the within the rock of the BGC rock. Then another this is a sigma type of grain tail complexes in the granites of BGC, and this is the minority foliation, and there is a grain there is a rotation of the quartz vein. There is a rotational component is there. So these features indicate that shearing has intensely happened in this particular area. Now talking about the evidence of mineralization in this block, this is the area where we got lot of evidence of mineralization within the Delhi supergroup rock, and the lower one is a lot of evidences are present in the BGC rocks, that is Mangalwar rock in the Mangalwar complex. So these are the evidences within the throughout the shear zone hydrothermal, the evidence of hydrothermal fluid activity documented in the Delhi supergroup rocks and Mangalwar complex also. And within the garnet mica schist of DSG rock, northeast southeast trending hydrothermal quartz veins were mapped during the mapping, and also some evidence of copper mineralization has been found in this lithoanite. And in this particular area, I have found out 1 kilometer long Gosan zone. Okay. So these Gosan zones not only restricted in that particular area, in this particular direction in the south also at some places the Gosan zones was exposed. And now this is the evidence of mineralization found in the Mangalwar complex of rocks, intense silicification, in situ malachite and azurite stain, as well as potassic alteration, intense oxidation, producing extensive iron oxide and magnetite, and presence of different association of sulfides, fresh sulfides are the positive evidence of surface indication of mineralization. Actually, it is taking a lot of time to change the slide. I don't know why. So these are the surface evidences of mineralization. If we see the photograph 1, 2, 3, photograph 1, 2, 3. These are the photograph of Gosan, which I have found in the northern part of the area, and 6, 7, 8 also photograph of the Gosan. 6 and 7 is showing the boxwork structure, and the 8 is brachia-like structure, and along the grain boundary of the brachia, I am finding some remains of sulfides and also some iron oxides, which I recognize it as a hydrothermal brachia. So if it is a hydrothermal brachia, definitely hydrothermal activity has taken place in the particular area. Apart from that, you can see the other evidences, lot of malachite stain. Malachite is a secondary copper carbonate. If primary copper ore is there, then only malachite and azurite will form. The malachite and azurite has formed extensively in this particular area. Apart from that secondary copper carbonate, I got fresh sulfide also, chalcopyrite, euhedral pyrite, and along with the chalcopyrite and euhedral pyrite, coarse grains of molybdenite also identified in the hand spacing of the in the field. So these evidences clearly indicate there is a hydrothermal activity and mineralization is definitely there below the surface of the earth. And these are the hydrothermal alteration in the study area. Different type of hydrothermal alteration has been identified. So first photograph is showing the potassic alteration, and second one is also potassic alteration along with the association of some malachite and some carbonate rock. Then again potassic alteration and albite vein, potassic vein. Then this EFG, these three photographs are magnetite. Extensive magnetite has been found to be associated with the granites of Mangalwar complex. So these extensive hydrothermal alteration and the surface indication mineralization clearly suggest that there are a lot of hydrothermal activity has taken place. And definitely some good mineralization may be there below the surface. Obviously, this gives you a preliminary idea. But after that, we have to do a lot of studies, subsurface study by using other techniques like geophysics, to see that whether the mineralization is continuing below the surface or not. But those are beyond the scope of work. That's why I am showing only the surface evidences. Now, if you see the chemical analysis, I have collected bedrock sample, channel sample, and analyzed, and I got up to 6,100 ppm of copper In the bedrock sample, in channel sample also I have collected 3 to 4 channels in the particular area. There I have got up to 5800 ppm of copper. Along with the copper, I have also found out gold, and gold value is varying from 50 ppb to 200 ppb. Though it is not very high, but still the presence of gold is confirmed by chemical analysis. And analytical value of molybdenum also varies from 5 to 393 ppm, and it is in bedrock sample, and in challenge sample up to 581 ppm molybdenum was recorded in chemical analysis. This shows that if the chemical analysis shows that definitely mineral is present. Now, ore petrography. I carried out ore petrography from the collected rock sample from those particular areas. Ore petrography also confirms the presence of chalcopyrite. Main copper ore was chalcopyrite. Along with the chalcopyrite, few grains of bornite also identified under the microscope. This first photograph is showing that the chalcopyrite is disseminated throughout the rock. And second one is showing that coarse chalcopyrite, and the rim structure is basically iron oxide. It's showing that the chalcopyrite is being oxidized gradually and forming the iron oxide. Then third photograph is also showing the presence of coarse grain chalcopyrite, and fourth one is showing chalcopyrite and pyrite association, fine and coarse association, and E and F. This photograph is showing coarse grain molybdenite, which is present in hand specimen also, and that was confirmed by the microscopic study also, one microscopic study also. And this G photograph is showing the alteration of chalcopyrite along the grain boundary. It is altering to bornite, and definitely bornite, chalcopyrite is gradually converting to bornite from the grain boundary. And the last one is association of molybdenite along with the chalcopyrite, pyrite, and other sulfides. So these are the laboratory support with the help of which I have tried to conclude that this area have some hydrothermal activity has taken place in the area, and mineralization has been taken place. And definitely after that I didn't get scope to study further, because that was my limit. Then after that exploration is going on in this particular area, in this particular time. They are trying to find out whether the mineralization is going below the surface of the earth, and they have drilled few boreholes. I think presently they have drilled 2 boreholes in the particular area. Those significant mineralization still not intersected. 2 boreholes has been completed. I came to know from the worker of GSI. He's saying that some mineralization in terms of chalcopyrite and pyrite they are getting, but they have not get big success in that particular area. But surface indication tells that mineralization should be there. So now let me conclude from the whole study. What can I say? The study concludes that the area is structurally very complex, and with signature of polyphase deformation and intense shearing along the contact between BGC and Delhi suburb rocks. Then the strike of foliation and the strike of surface mineralization is same, because whatever the mineralization I have found, they are either parallel to the S2 foliation, or they are parallel to that particular northeast southeast direction. So we can say that this is a structurally controlled, because if it is structurally controlled, then only it will come parallel to the foliation and structure. Now, occurrence of mineralization within the extent of shear zone, as what is in my observation, those evidences of mineralization was restricted within particular shear zone rock only. Beyond the shear zone rock, there was no evidences. So definitely shear zone plays a very important role in channelizing the ore bearing fluid. So that is my conclusion, that shear zone points toward the fact that the shear zone acts as a major channel or pathway for transportation of the ore bearing hydrothermal fluid and deposition throughout the shear zone rocks. And again, the presence of boson in the northern part of the study area suggests that there is supergene enrichment has been taken place for copper and associated economic minerals. Obviously, IOCG, as Panigrahi sir was telling it was a myth, then I was sitting there thinking, should I tell it is a IOCG? So whatever the evidences, surface evidences I got, it may lead to the conclusion that this might be a IOCG type of mineralization. Definitely for that we have to do a lot of study. And
Thank you, Mr. Devnath.
Yes,
you can
sir.
have only 2 questions. Any questions if somebody has it?
No, sir. Quartz was also there. Silicification was also there. Quartz was also. Yes, sir. Yes, sir.
Anybody? Some small questions we can take.
Yes, sir.
Sir.
Yes, sir. They have planned shallower boreholes. Deep borehole. That was my suggestion also, because yeah, they are doing 60-meter vertical intersection, because we should go deeper, I think. Yes, sir. Yes, sir. Yes, sir. And things that. Yes, sir. Yes, sir. Yes, sir. Yes, sir. And I think detailed geophysics is also required in this particular area. And after doing the detailed geophysics, we should understand the nature of the mineralization. Then we should go for deeper borehole.
Okay. We can.
Mineralization zone, the Gosan zone is 1 kilometer long. And the evidences, what we have found, that is also 400 to 500 meter area. It is no, outside the shear zone, there is no evidence of mineralization. Only whatever the evidences was there, they were restricted within the shear zone only. So I think this shear zone need to be studied in detail, then only we could find something, sir.
Okay, thank you.
Okay, thank you, sir. Thank you all.
So you can continue with the other presentations.
Now I request Kanya Chaudhary for his for presentation on post-magmatic alteration and textural evolution.
This is the one, no?
Yes.
Second. Share the page.
Good afternoon. I'm Sukanya Chaudhary from State Unit Andhra Pradesh. I will be presenting the post-magmatic alteration and the subsequent textual evolution of chrome spinel from Ramgiri Greenstone Belt, Andhra Pradesh. So the left. Ma'am.
There I have asked them to.
The left-hand side map is a generalized geological map of Dharwar Craton in the southern part of India. Dharwar Craton is divided into three domains, western, central and eastern, demarcated by two deep crustal shear zones, Chitradurga shear zone and Hatti Kadiri Kola shear zone. Our study area lies within the central Dharwar Craton in and around Ramgiri. The right-hand side map is a generalized geological map of Ramgiri Greenstone Belt. Ramgiri Greenstone Belt is a linear north-northeast, south-southwest belt trending for about 100 km with width varies from 200 meter to 8 km. This belt is characterized by bimodal felsic and mafic volcanics, with the mafic volcanics more dominant. The mafic units are represented by metabasalts and amphibolite and their altered variant. The felsic volcanics are subordinate and patchily distributed. They are represented by meta-rhyolite pyroclastic materials, felsic tuff, and their altered product. There is abundance of pillow basalt, which along with quartzite, BIF and chert horizon indicate a subaqueous volcanic setting. Linear ultramafic bands are located in the southern segment of this belt. So in the southern segment of this belt, these linear bands occur as thin discontinuous band with width varies from 0.5 meter to 250 meter with a lateral extent of about 5 km. The metamorphosed ultramafics are include altered dunite talc schist, and they have disseminated chrome spinel, magnetite and ilmenite in it. So the altered dunite in this ultramafics, they are massive melanocratic medium grain, primarily composed of relict olivine and serpentine, which occur along the grain boundary and the fracture plane due to hydration process. And this have disseminated chrome spinel in it. The chrome spinel show a typical core rim structure. Elemental X-ray map has been done of this chrome spinel, and they show a typical chemical change across a spinel grain. The Fe is more concentrated in the outer rim, whereas it is depleted in the core area. Chromium has a high concentration in the core portion and decreases outward. Similarly, magnesium and aluminum also decreases as we move from core towards the rim. Talc schist is a leucocratic medium grained rock, has a soft soapy texture composed of talc with very few relict pyroxene and secondary carbonates like magnesite. They also have disseminated chrome spinel throughout their ground mass. A similar X-ray elemental map of a chrome spinel from talc schist has also been done, and these show the similar kind of chemical change as that of in the altered dunite. So the spinel in both the ultramafic units have a common core rim structure, and they are surrounded by a silicate matrix mixed of chloride, talc and serpentine. The chrome spinel were analyzed and the elemental data were plotted in CRAL Fe+3 ternary plots. Upon plotting, it was seen that none of the core composition fall within the field of primary spinel, which indicate absence of spinel which has a primitive composition. But a texturally preserved cores are seen, which is now modified. This core is surrounded by a rim 1 and which is further mantled by rim 2. So across the spinel grain, Mg, Mn, Ti and Al show a sharp decrease. Fe+3 sharply increases as we move from core to rim. NiO and Cr also increases gradually as we move from core towards the rim area. The elemental data were plotted in several binary plots. The blue points are the core composition, which are now modified. Green points are the rim 1 and the red one are the rim 2. Mg and Cr show a negative correlation with Fe+3 by total Fe. Minor oxides like TiO2, MnO also show a negative correlation and decreases as we move from core towards the rim. NiO on other hand increases as we move from core towards the rim and shows a positive correlation. So the alteration sequence of this chrome spinel starts with hydration, followed by the chloritization and then a magnetite overgrowth under a progressive oxidizing environment. So let's assume that there is a primary spinel surrounded by a matrix of olivine and pyroxene. The alteration starts with hydration and serpentinization. So forsterite reacts with water and forms serpentine and magnetite. This magnetite is formed due to the release of excess Fe during this serpentinization process. The next stage is the chloritization in a progressive oxidizing environment. So the chloritization event is accompanied by volume reduction, which creates pore space, and these pore space are filled with chloride. So during this transformation, Fe+3 and Cr is depleted from the core, and they are more concentrated in the rim area and show an enrichment. And MgO on other hand decreases. So the reaction is the primary spinel reacts with the silicate and gives chloride, and an altered spinel which has a modified core surrounded by a rim 1. So now as the chloritization progresses, this chromite grain is surrounded by a chloride mantle, because these are the sites from where the chloride can get aluminum and Mg from. In a spinel general formula AB2O4, A site, the tetrahedral site, has Mg+2 and Fe+2. B site has Fe+3, Cr+3 and Al+3. So during this chloritization process, the chrome spinel undergoes a transformation from the modified core to rim 1, and it loses aluminum and magnesium to form chloride, which in turn increases the chromium concentration. And in an oxidizing environment, Fe+2 gets continuously oxidized to Fe+3. So the chrome spinel reacts with serpentine, water in an oxidizing environment and gives a ferrium chromide, which is rich in Fe+3 and chloride. So during this transformation from core to rim, Mg number and aluminum decreases, which leads to an apparent increase of Cr number. Fe plus 3 by total Fe also increases, and so does Fe number. On other hand, minor elements like TiO2 and MnO decreases from core towards the rim, because TiO2 gets preferentially mobilized during the serpentinization process, and it gets removed by the circulating fluid, and it does not readily fit into the new evolving chromite structure. So it is depleted in the rim 1 area. NiO increases because during the oxidization process, Fe plus 2 gets oxidized to Fe plus 3, and this creates a vacant site in the A site. So that site is filled with Ni plus 2, and hence it increases in the rim area. So chloritization event is responsible for the formation of a ferrium chromite rim, which is our rim 1 around the modified core. Now, generally, this alteration terminates with rim 1, but if the oxidation continues, the alteration progresses further. The interconnected pore space created during the chloritization event, which is now filled with chloride, facilitates the circulation of Fe-bearing fluid. This fluid then dissolves the chloride and precipitates magnetite in its place, and it is chromium rich, and hence it is termed as chrome magnetite, which is our rim 2. With extreme chloritization, the original spinel structure gets obliterated, and the spinel chemistry changes to chrome magnetite. And with the advancement of the oxidation, the chrome magnetite gets martitized to hematite. So this marks the final stage of the progressive oxidation event and signifies the end of spinel alteration. So this is how a spinel chemistry changes in a fluid-mediated alteration process under a progressive oxidizing environment. Thank you. Yes, sir. Thank you. Yes, sir.
Okay, let us proceed to the next.
Yes. Thank you, sir.
Presentation is on the evaluation of porphyry style hydrothermal copper molybdenum lead silver mineralization in Amirgarh by Rana Bandopati.
गिरेगा तो नहीं
Yeah.
मेरा अरे यही है ना हाँ ठीक है हाँ
Good afternoon, everyone. I am Rana Bandopathy, Geology, State Unit, Rajasthan. I will be presenting on the topic. Probable, I should have put a question mark on the porphyry style, but definitely hydrothermal. Copper molybdenite, lead and silver mineralization in Hamirgarh Chittargarh area of Rajasthan. This is the study area continuing from Hamirgarh to Vienna. Actually, the work is a part of regional mineral targeting work we have carried out in the field year 2022 to 2024. Okay, so these are the different data sets we have used during the regional mineral targeting data. The area of question are marked here in the yellow ellipse. There are aeromagnetic data was there along with spectrometric data and gravity data from NGPM surveys. And from ASTER data, we have done extraction of lineament and some alteration work, and the mat have been put here. Okay, so after considering all those data sets and preparement of different buffer maps. We have done a prospectivity modeling or favorability map to locate new zones of mineralization, and those areas marked by the red color are the most prospective based on the data set, and that was definitely a knowledge based model, not a data based model. So the area in question is dominated by the Berach granite along with and related intrusions and phyllite rock of Hindoli group. At the very left side, this is the typical Berach granite outcrop which we encountered during the field. And this is the second photograph is of silicified quartzite. This is not a quartz reef. This is a silicified, highly silicified quartzite. The quartzite actually belong to the Lazadia formation of Mangalwar complex. And there are some volcanic rocks associated with the Berach magmatism probably that we have encountered during the field. These are the all rock type we have encountered in the field work. So as we are discussing about the mineral system and also the mineralization in the work we have identified mostly within the Berach granite. So I just put a reference from a paper from Singh et al. That how the Berach granite came to exist. And the Berach granite was in place around 2.6 GA during the subduction of Bundelkhand craton beneath the Marwar craton. And the paper from Mondal et al. Says that it was formed by partial melting of a metasomatized subcontinental lithospheric mantle, and that's why it is a hydrous and oxidized magma, and that may be enriched in matter from the mantle origin and have enough amount of fluid to be generated which can carry metal. So these are the alteration signatures we have found in the field. Actually, we haven't done the actual alteration front mapping during the field work. We collected the sample after getting the chemical and thin section done. We have found out that this kind of zonation of the alteration pattern is there. So we try to put them up in a sequential manner. Yes, sir. Okay, sir. So this is the core zone where extreme amount of K alteration have been there, and the second photo is from a drill core along which we are getting copper mineralization also. The second zone, the phyllic zone, is dominated by sericite quartz mineralogy, and the third zone, the propylitic zone, is dominated by chloride carbonate, and some cases there is some pyrite with this lithology also. So these are the evidences of different types of alteration, silicification, mineralization associated with quartz reef, mineralization associated with epidote alteration, brecciation of or hydrothermal generation of hydrothermal breccia, and there are association of molybdenite have been found along with the potash alteration within the granite. The breccia within the core we have found they are also hosting the copper mineralization, and in the quartz reef we have found substantial amount of concentration of silver up to 145 ppm, and it forms a zone of around 9 meter with 45 ppm of silver. So based upon the targeting of prospective drilling target, we have drilled some borehole, though very lean, but we have get some enriched zone of copper mineralization associated with K metasomatism, I think, because secondary biotite and alkali feldspar have been formed there, and chalcopyrite is also associated with it. And these are the some photographs of the drill core along which the chalcopyrite mineralization associated with the K-rich rock within the granite. Also, other than copper, we have also got presence of, probably this is a hydrothermal lead, silver is also associated with. So we're getting the, though we haven't found any particular silver mineral in the thin section of that, but they may be within the lattice spaces of other mineral, but in the chemical data we got a substantial amount of concentration of silver. Fluid inclusion study was also done. Dominant inclusion were primary biphase aqueous solution with low to moderate salinity, and homogenization temperature also varied widely from 120 degrees centigrade to 257 degrees centigrade. Isochrons are intersecting, and evidence of immiscible fluid maybe suggest towards a prolonged fluid activity or pulses of fluid activity in the area. स्लाइड चेंज नहीं हो रहा. Okay, okay, done. So now for geochemical prospecting in porphyry kind of deposit, though we are not sure about the type of deposit in it, there are lots of porphyry indicator mineral which are present and that have been proved in the same study. But unfortunately, the trace element geochemistry which differentiate it from the magmatic to hydrothermal origin is not available with us for right now. But that study may help in future vectoring and establish a genetic linkage between possible porphyry type of mineralization with the help of this porphyry indicator mineral. So in conclusion, though it's a very primitive one of model, so we have got not basically we haven't sampled it keeping in mind to establish a porphyry kind of deposit. We sampled it to establish a zone of mineralization. After the analysis and thin section done, we are getting this kind of zoned alteration pattern in where the potassium rich core is bounded by a phyllic zone with epidote chloride and carbonate assemblage, and then a propylitic zone, convergence sericide dominated phyllic zone, then a propylitic zone dominated by epidote chloride carbonate assemblage. We are getting the oxide remnant of the silicic lithocap. Those are goethite Gaussian have been from there, and the remnant silicic lithocap is also present in the form of chart and charty breccias. So what will be the future work we can done with it? The mineralization is mainly hosted within the fracture system. This is the map in the left corner of the slide is the tilt derivative map of that area, tilt derivative map of the aeromagnetic data. The what tilt derivative map does is it basically picked up the edges of fractures, faults or lithological contact. So we can see that there are cross-cutting northwest southeast and northeast southwest linears are present in that particular area. So this area may act as a trap for the mineralizing fluid. So structure density mapping in field taking account of all the available fracture data will help us establish the geologically dominant fracture pattern, and we can match it with the fracture pattern derived from the TDR map. And then alteration front mapping, our focused alteration front mapping will help us to deduce the possible drilling targets, and then the trace element geochemistry from LAIC PMS of the different porphyry indicator minerals will help us in future vectoring. Thus, at the end, with all the data by geophysical inversion modeling, we can fix a deep drilling target which can possibly towards more thicker enriched zone is there, but those are lean zones, thicker zones of mineralization. Okay, that's all. Thank you. Yes, sir.
Yes.
Porphyry indicator mineral, actually this, the trace element geochemistry of this mineral differentiate between the magmatic mineral and the hydrothermal mineral. Porphyry indicator mineral in published literature, these minerals are associated with porphyry systems. Zircon, apatite, feldspar, epidote. Yes, sir. So the trace element geochemistry is required to differentiate that particular method, sir. The trace element geochemistry of that particular mineral phases is not available with us right now. Yes, sir. Basically, when we start, yes. No, sir. % NaCl equivalent and 260-degree temperature centigrade. Sir, there are already established two phases of granitic activity. In older literature, it has been said as the gray one and the pink one. One is alkali feldspar, another one is feldspar. Yes, sir. So that question also arises when I take the fieldwork there, because before the Bindan Basin came into being, the two areas were similar. So when I getting so much a large deposit over in Malanjkhan, and in Beraj granite we are getting similar kind of large quartz reefs. Why not to try for this kind of mineralization here? Yes, sir. No. Yes, sir. Yes, sir. Yes, sir. Yes, yes. Yes, that can also be, sir. Ye- Yes, sir. Yes. Because, sir, in the sir, there is an area named Devtalai, around 30 km northeast of this area. There is a established copper prospect, copper and gold prospect there, and their mineralization is also hosted within the quote unquote pink variety of Beraj granite. Yes, sir. Yes. Yes. Yes, yes. So that's why I said that this is one of our my vectoring tool. I will not only depend on this area. We are basically taking a mission to RP project. Mission 2 we will deal with the mineral exploration item. So we'll do everything. We'll do every aspect of starting from that geochemistry aspect, geophysical aspect, and structural mapping also, sir. Thank you, sir.
Thank you very much.
The next item will be genesis of sodium metasomatic uranium deposits of North Delhi Fold Belt by Priyanka Mishra.
Sir, I think the presenters have not come yet.
Okay.
So we'll move on with the next
Go to the
presentation.
next one. So petrogenesis and geochemistry of tourmalines from the Archean Ramgiri goldfield by Arijit Bali.
Hello. Okay. So good afternoon all. I'm Arijit Barik, Senior Geologist, Geological Survey of India Southern Region. So respected Chairman, Co-Chairman, Delegates, and co-participants. So it's an honor to show a research work over here. So today I'll be discussing about the microscopic chemistry of a mineral, which is tourmaline, and how we used as an ultimate forensic witness to reveal the source as well as the nature of the gold mineralizing fluid. So I'll be talking about tourmaline. As all of you know, that tourmaline is a structurally complex but stable borosilicate mineral. It's because of its chemical diversity as well as widespread occurrence, particularly in the hydrothermal system, makes it an invaluable petrogenic tool to characterize the mineralized fluid. And also, if you study the boron isotope of tourmalines, it will help to distinguish the fluid source. So, in essence, you may say that tourmaline acts as a geochemical archive. So, So going further, my presentation has been structured into 6 parts. First is introduction, followed by field characteristics in petrography, geochemistry, then stable isotope studies, and finally concluding remarks. So gold deposits dominantly in India are hosted within Archean greenstone belts, particular within the greenstone belts. Sorry, in Archean orogenic setup, particularly in greenstone belts. So in Dharwar craton, tourmaline is associated with gold in many of the lode gold deposits. But if you see the Ramgiri Peninsula system, which is present in the eastern part of the eastern Dharwar craton, hosts the Ramgiri gold deposit. The gold occurs within this in the Ramgiri Peninsula cyst belt within metavolcanics and metasedimentary sequences, which is structurally controlled by CO zones. So our study area is confined to this central part of the Ramgiri Peninsula cyst belt, from where we have collected samples from the proximal part to distal. Proximal means proximal part of the gold deposit to distal part. So these are the field photographs. The first one is the field photograph showing various alteration zones along the CO zone. And we have observed silicification or chloritization, carbonatization, as well as silicification along these CO zones, which is typically of a orogenic gold setup. And these are the field photographs of showing close association of quartz as well as tourmaline along these CO zones. And this close association of quartz as well as tourmaline, it gives the initial impression that the gold is associated with tourmaline. So here we have carried out petrography. So in the left side, these are the photomegraphs of tourmaline and quartz association. Here you may see different generations of tourmaline. So tourmalines, one is pre-deposition and other is post-deposition, you may notice. And we also carried out same study, and these are the BSE images. And the lower one, the center lower one, if you see, so this BSE image also displaying the close association of quartz, tourmaline, and gold. And gold in this area is occurring as a free milling state as well as alloy of copper and gold. And the gold is not only associated with tourmaline, it is associated with pyrite phases also, sorry, sulfide phases also. And so from this we can know that we are able to know that the mineralization is polyphase, and gold is hosted in the quartz calcite tourmaline rutile veins. Another thing you may notice here is that the gold is occurring as an alloy with copper, as well as arsenopyrite is occurring. The composition of the arsenopyrite is nickel chromium arsenopyrite. From this, you may say that the source is a mafic one or ultramafic one. So these are the photomicrograph. This one is gold within quartz vein, and these are the other sulfide phases occurring in the area. So now coming to the mineral chemistry, we have performed APMA to characterize or to know the fluid source. So you may see here, so all the samples are falling within the dravite classification of tourmaline as well as alkali group, which get typically of orogenic gold deposits. And from this we can show that from this composition, that the setup is orogenic gold deposits and the source is hydrothermal driven by metamorphism. And also, here another thing I would like to emphasize is that dravite, which is a Mg-rich tourmaline. Mg-rich tourmalines, when it will form, when it will either the fluid is interacting with the host mafic body or the source is mafic. We have also performed LA-ICP-MS to know how the trace elements are behaving within tourmaline. So these are the discrimination plots, which all the samples are falling within the hydrothermal metasedimentary fields. So samples are not falling within the magmatic field. Here also some more discrimination plots. Here also samples are falling within hydrothermal field as well as metamorphic field. And if you see the first plot, barium versus strontium by SN, so here you see the samples are not falling or not belonging to barium rich environment or say barium poor environment. So this is an indication that there is a mixing of fluids. So from this, we are coming to know that okay, the fluid source is hydrothermal driven by metamorphism. So now coming to the isotopic characterization. So here you see the first one is boron isotope study. So the boron isotope is varying from minus 14 to up to plus 4. So here I would like to tell that the negative values of boron isotope means the source is metamorphic, and the positive minus 3 to up to 10. So that belongs to the magmatic source, and more positive values are belongs to carbonate or say marine carbonates. So here you may see that most of the samples are falling within the negative field. Here I would like to emphasize is that some of the samples here less than -7. So these samples are from proximal part of gold deposit, and these are distal part. So that means the proximal part of Ramgiri gold deposits, the source is showing metamorphic source, or say the fluid source is metamorphic. And here, the fluid source is magmatic. So this is one we have to look into this. And the next one is sulfide isotope values. And sulfide value, if you see this sulfide isotope values of Ramgiri central belt, so it is near to 0 or little bit varying from 0. So this means the sulfur source is metamorphic source, or sulfur source is metamorphic. Now coming to the carbon and oxygen isotope value, here you see the carbon isotope value is fluctuating, or say it's ranging from negative 6.5 or something like that to 3. So this high range is because of the fluid mixing. So from all these isotopic values, we are coming to know that the source is metamorphic, and not only that one, this high range of values are coming because of the change in redox condition and fluid mixing. So this is the proposed mineral system. Source is metavolcanic source, and which has undergone metamorphism and fluid release, which already we had evident from the geochemistry. Then the fluids were catalyzed by shearing effect, and fluid rock interaction also gave tourmaline, which is Dravet type. Dravet type means interaction is either with a mafic source or ultramafic source, or the source is mafic or ultramafic. Then after that, deposition and preservation. So there is lithological trapping, as we are getting the gold as well as sulfide within quartz carbonate tourmaline veins. Then finally, the preservation is gold sulfide deposition. So now about concluding image. So we have seen the field observation as well as the petrography and geochemistry. From this, we are able to know that there is a genetic association between gold and tourmaline. And the geochemistry signatures, they point out the hydrothermal orology largely driven by the metamorphic fluid. And the tourmalines are predominantly dravite belonging to the alkali group. The formation dravite indicates to fluid source as MG-rich fluid or interaction with MG-rich rock. And finally, the stable isotope data, they are indicating a mixed metamorphic hydrothermal field source. So this is the conclusion.
Thank you, Mr.
Thanks.
Arijit. I think for any questions, you can have a personal discussion with him. We have to go immediately for the next item because we have to vacate this hall for.
Thank you, sir.
Yeah, the next presentation. Polymetallic mineralization. RE, titanium, strontium, ionium, vanadium. Just show the ultramafic complex. So, an interplay between magmatic and late stage carbonate metasomatic systems by Hrishikesh H.
Yes, sir, sure. evening to all. Am I audible? Yeah. So, I'm Dr. Rishikesh from State Unit Assam. So, I'll be presenting polymetallic mineralization in Jeshra ultramafic alkaline complex, a complex interplay between magmatic and late-stage carbonatite magmatic systems. So, I'll quickly go to the main topic. Let me start with the regional geology of the Shillong Plateau. So, Shillong Plateau is located in the northeastern part of the Indian subcontinent, where we can see, this is the Shillong Plateau, where we can see the entire area is covered with the Archean Proterozoic gneissic complex, followed overlain by Shillong group of metasediments and further included by granitoids. Yeah, further included by the granitoids. The last stage of the magmatic activity in the Shillong Plateau is represented by the Cretaceous ultramafic alkaline complexes, which is marked as 1, 2, 3, 4 here and 5. And our study area is number 3, that is Jeshra ultramafic alkaline complex. Now coming to the brief geology of the JUAC. As I said, it's an ultramafic alkaline complex. So it's dominated by the ultramafic rocks. The dark green color portion is basically the pyroxenite, and the light green color is the gabbro. Other than that, we have the alkaline suite of rocks, that is basically cyanite, aeolite, and some unusual occurrences of perovskite magnetite cumulates is seen within the pyroxenite body, which actually spreads over a 3.2 square kilometer area. And before proceeding, we can say my work is mainly focused on the pyroxenates of the area, which is highly phenetized due to the late stage alkaline as well as carbonatite metasomatism. Now coming to the field observations. So since I told you it will be focusing only on the pyroxenate. So from the field observation itself, we can see the pyroxenates cut by numerous carbonatite veins. So this is one type of pyroxenate we are getting. One is completely metasomatized, which lost its original characters completely. And other type of pyroxenate is having the cumulates of perovskite and magnetite. You can see, you can appreciate the same thing in the zoomed up image, where we can see the silvery appearance portion is basically the clusters of magnetite and perovskite. Other than that, we have a enriched regolith profile as well as laterite, which is seen in the bottom photographs. And if you see, this pyroxenate is completely weathered. That magnetite perovskite cumulates is residual, and you can see it as a small continuous layers within the regolith profile. So coming to the geochemistry of these complexes, we can see the pyroxenites is having total Re concentration as low as 100 ppm to as high as close to 12,000 ppm. Titanium up more than 3% up to 22%. And niobium up to 14,400 ppm. Vanadium more than 500 ppm. And strontium more than 1,000 and up to 30,000 ppm. Now coming to the weathered profiles, we have Re up to 0.9%, niobium up to 3,000 ppm, vanadium up to 2,500 ppm, and titanium up to 42%. So this is the basic chemistry what we found in these rocks. Now to understand what would have contributed to these high-end values. So the primary phases, as we know, pyroxene is composed of CPX. So the 70 to 80% is basically CPX. Other than that, we have the peculiar mineral, perovskite, which is the mantle mineral, having CaTiO3 as a structural formula, which is seen as occurring interstitial spaces or occurring as a cumulates. Here you can see the clusters of perovskites are seen within the pyroxenite. Other than perovskite, within the perovskite, we have some secondary alterations of enrichment by converting into loperite, and this is actually lucite. And this, when we see about the cumulates, basically the scene which I have shown before, the cumulates are basically only composed of perovskite and magnetite. So that can be appreciated from the field photograph. And if you see the chemistry of the perovskite, you can see that it is basically falling in the pure perovskite region, having 1.5 to up to 3% of Re in their crystal structures. Other than that, as we all know, perovskite is rich in titanium, so 50 to 60% of titanium is contributing from the perovskite itself. And niobium in this crystal structure, basically NaNbO3 is this lucite portion. It is having up to 0.3 to 0.5% of niobium content. And you see the second most important mineral, that is magnetite, is contributing 1 to 4% of titanium, as well as vanadium up to 0.4 to 0.8%. And ilmenite is contributing the remaining titanium. So these are all about the mineral chemistry. So that what we have discussed right now is about the perovskite-rich pyroxenides. Now if you see the metasomatized pyroxenite, which I was telling where is intersected by a lot of carbonate veins. So this is basically an alteration zone. You can see these are CPX, this is the calcite vein which has intruded into the pyroxenate, where we can see small phases which is identified as apatite, basanesite, pyroclase, strontianite, and ansilite. So these are the mineral chemistry plots. Now, to understand what is the contribution of these various minerals to the total Re, niobium, strontium, titanium budget of this rock, we have done point counting, which is a very normal Mayow method. We have done at 1,000 points, but patiently done in that area. And other than that, we used BSc mosaic images, and by using ImageJ platform, we tried to find out what may be the amount of each minerals present in these rocks. So we found that for pyroxenite, 70 to 80% is CPX only. The perovskite percentage ranges from 6 to 8%. If you add this perovskite and its contribution, integrating its contribution, mineral chemistry, as well as density, we found that the LRE contribution of this whole rock is contributed by 50 to 64% is by perovskite itself. And niobium, if you can see, 45 to 60% of the total niobium concentration in the whole rock is contributed by perovskite. Now coming to the magnetite perovskite cumulite. Here the more than 85% of the Re concentration is contributed by perovskite, and about 85% is contributed by niobium also. Since other phases actually very difficult because of the micro sizes, 20 micron, 10 microns, it's very difficult to go for a pointing counting. We will miss that. For that, we did some X-ray elemental maps and found that they're close to 1% in the rock system, and we found that they are contributing the remaining portion. The same thing, what I have seen is shown is a bar graph. The same thing, what I will explain right now. Other than that, we have strontium, which has sold up to 30,000 ppm, which is actually solely contributed by strontianite and ansilite in this rock. Other than that, the vanadium is contributed to the only sold mineral, that is magnetite. And titanium, as I already explained, perovskite, magnetite, and ilmenite is contributing to it. So quickly going to the mechanism. What would be the mechanism for the enrichment in Jeshra? So as I told, these rocks are rich in titanium more than 3%, and up to as high as 22%. Now, we have to think about a magma which was very rich in titanium. And I said earlier, it is having up to Re percentage up to 12,000 ppm. So again, it should be an enriched magma where this primary crystallization might have happened. So the primary crystallization and segregation and fractional crystallization and density separation of this perovskite and magnetite has led to the cumulate structures, which is actually seen in this thing, in this pyroxenate. So that is the first stage of enrichment for the Jeshra ultramafic alkaline complex pyroxenides. And the second stage of enrichment happened due to the carbonatite and alkali veins intrusions, where we can see, as I said, strontianite, ansilite, all these things are basically confined to the carbonatite veins which is present in the pyroxenite. So that creates the second stage of enrichment in the pyroxenides. Now, as I said earlier, the regolith is further enriched in the Re. So what would have happened? These two has weathered, and the chemical alteration index was so high, and it has leached out the entire CPX, all the silicate phases, and remaining the refractory minerals, basically perovskite, magnetite, was became enriched in regolith, further giving the high percentage of up to 0.1% of Re in these rocks. So that's the mechanism. So as a tail end, Geological Survey of India, we have done G4, G3, and G2 stage of exploration here, where we in G4, I was so fortunate that I was a part of G4 to G3 and G2, along with my field partner Tapan Patwari sir. So in G4, we have demarcated 3 square kilometer area, a potential zone. Further, we drilled in G3 stage, 200 into 200 meter drilling, and each borehole was 60 meter depth and as high as 120 meter depth. Now, currently, the work is in the G2 stage, and it is in 100 into 100. Total 123 boreholes we are drilling right now, and the deepest borehole was planned to 300 meter. So this is the basic drilling plan, what we have done. and this may, like we are almost going to finish this project by December, to give a glimpses of the resource estimated during the G3 stage of investigation. So here we can see we have two resources. One is basically from the regolith as well as the pyroxenite host rock. You can see a total of 28 million ton is the net output from the REO from the Jashra pyroxenite. If you see the titanium, it is having 138 million ton, where regolith was having 7.7% of the average grade and pyroxenite up to 4.35. Now, if you see the cutoff as niobium, the average grade is 766 ppm and 475 ppm, respectively for regolith and pyroxenite, and total of 45 million ton. Coming to strontium, yeah, cutoff value was taken as 1000, and this is our 62 million ton in comparing with regolith and pyroxenite. And we have a near to equivalent 2 million ton deposit in Jashra for the vanadium. So these are the resources we estimated from this. So we can say the mechanism itself actually says that a complex interplay of the primary magmatic followed by a late stage secondary alterations lead to the enrichment. Further, weathering leads to the total RE block of this area. So that's all. Thank you.
Hello. Thank you.
Yeah.
Thank you very much. Any questions? We can take one or two questions if.
Again, I would like to say, sir, this is one of the unique work we have carried out, because these kind of, yeah, we have carbonatite as well as ultramafic alkaline complexes from the Sung Valley, all these things. But this is having unique property because it's a perovskite hosted RE mineralization. Yes, sir. Yes.
Okay, very good.
Yes.
Thank you very much.
Thank you so much. That was very interesting. Any questions regarding this very interesting topic? Okay, if there's no questions, then I will just thank you so much.
Okay, thank you, sir.
Yeah, we'll just summarize the entire proceedings today. So, am I audible? Yes, actually, initially we had a very interesting keynote from the very distinguished professor from IIT Kharagpur, and Professor Panigrahi. Professor Panigrahi essentially, discussed an in-depth, discussion on the interplay between your mineral systems regarding the orogenesis versus exploration. He basically said both things go simultaneously and hand in hand. And many of the deposits actually were understood after the exploration took place, and rather after the mining took place. So it's an ongoing process, and it was quite summarized and effectively, argued that these two aspects, right, we in GSI actually do the exact same thing. We do the exploration and we understand the mineral deposit. So maybe what he essentially in the keynote address, what he mentioned was very pertinent, especially for exploration agencies like GSI, where we do the exploration, we understand the mineral deposit. So that was the starting point of, where we started with this technical session. And after that, we had a number of speakers. Everyone gave very interesting, examples of mineralization, and starting with the Sanjay Debnath, who gave a very nice, field-based and petrography related, study on the structurally controlled hydrothermal copper molybdenum gold mineralization in the granite gneiss of Mangalwa complex. What I felt was quite interesting was at the outset itself, he said it's a field-based study, and he has given a very wonderful field photographs, as well as all those photographs about the Gosan and other things. And it was very actually we said the pictures speak 1,000 words, so it was all self-explanatory. And especially interesting was the potash feldspar magnetite alteration, which is also sometimes closely associated with IOCG, although he didn't mention that it was, he of course let it open for us, for later studies to be deciding whether it's IOCG or not. But of course it had very close similarities with IOCG in terms of the K feldspar as well as magnetite alteration, and also the copper molybdenum gold association. So after that we had the post-magmatic alteration process and textural evolution of chrome spinel an interesting example from the Ramgiri schist belt. And this was given by Sukanya Chaudhary, and this was an excellent presentation. And even here, she has given a beautiful, photographs of, thin section photographs of chrome spinel, which was, you can see that zoned alteration, which was, the chrome spinel was essentially altering into ferrite chromite with more, iron-rich, rims. And there she explained the process of hydration, chloritization, which enhances, the hematite and magnetite, and later the hematite or martitite alteration. So what I felt, even in my experience with some of these minor, experience in Attapadi Valley and other ultramafics where I study the chrome spinel, it is essentially the same thing. Most of the chrome spinels are highly altered, and they don't essentially preserve any of the magmatic textures. But all these beautiful, hydrothermal alteration and hydration and serpentinization textures are wonderfully preserved. And she has done this work, and this systematically documents the process of alteration of chrome spinels. And that was really a wonderful, example of a study. Later on, we have a porphyry-style hydrothermal copper molybdenum lead, silver, very interesting topic by Rana Bandopadhyay, and it was it had close similarities with Malanchkan, although it has to be, maybe it's a porphyry style or not, that is yet to be done, but he gave an interesting example. And what I found interesting was that the granite which was having this deposit was classified as sanukitoids, and we all know that sanukitoids are very specialized magmatic rocks which are formed in subduction zones. And in these subduction zones, we get granites essentially enriched in MgO as well as K2O, a very clear indication of magmatic mantle component. So it is in, these are basically highly enriched and what we can say fertile magmatic rocks which will essentially contain gold and copper mineralization. So there is a clear correlation between sanukitoid magmatism and copper gold mineralization worldwide, and maybe this is one of the case. And what I would advise him is that I found that he had a lot of monazite in this study. So it would be interesting if he can do some EPMA monazite dating to exactly fingerprint the timing of the gold, or rather the copper mineralization. After that, we had the very interesting study by Arijit Barik and team regarding the tourmalinites and tourmaline from the Ramgiri gold fields. And essentially, he has demonstrated that the gold mineralization, rather orogenic gold mineralization, essentially formed in quartz tourmaline sulfide veins. And they are very closely related to regional scale alteration systems. And he has correlated this with other major orogenic gold deposits. And even in my experience, I have found that whether it's in the Chitradurga schist belt, or whether it's in the Ramgiri or in the Hatti and other places, tourmaline is closely associated. And he has classified it as dravite, and he has said that the significance of Mg-rich tourmaline, which is essentially maybe an interplay or relation with the mafic rocks or the metasomatic alteration involving magnesium. So that was indeed an excellent study. And after that, we had last but not the least, a very, very interesting study from the Meghalaya. I think it was the Shillong Plateau with the polymetallic Re mineralization. Maybe it's a carbonatite associated alkaline system. And what was very interesting was the very extremely high Re and other niobium and other values, which are I think maybe the way forward for GSI, because here we have the parent rock which is enriched in Re, niobium and everything. And he has also demonstrated that there is a regolith which is much more enriched, close to 3000 ppm Re. So this is quite a significant body. I think that body, I remember, was 3 kilometer by 3 kilometers. So if he's drilling and having a 30 million ton resource. So this is something quite significant, and I really congratulate Mr. Hrishikesh for showing us an excellent example of Re enrichment in regolith, because that's quite significant, because this is possibly, I don't know, it's the extension of the Myanmar orogenic belt or something, which they have a lot of, South China and Myanmar. They are essentially the world's most richest source of heavy Re, and most of them comes from granites and regolith. So this is close to that. So maybe this is something new for GSI, and thanks very much to Hrishikesh. And That's my overall summarization. Now I hand over to the chairman of this committee for his comments.
I am really delighted to have been here during the presentation of such an exciting topics, and particularly Rajasthan base metal deposits and VMS systems and hydrothermal alterations, because it reminds me a lot of my days when I was working here in Rajasthan, and really I am enlightened by the latest developments in all these projects. And of course, as he has, Praveen has told that this RE concentration in that Meghalaya plateau, it's really very interesting, and it needs a lot of traction. And particularly in the first lecture by Professor Panagiri, I must add that people say that GSI has done a lot of work in the last 175 years. And now at least we know that what type of deposits we are tackling. So we should have a conceptual approach in all the exploration programs. Say for instance that BMS deposits and SEDEX deposits, if we are having that model, then accordingly we have to search for those type of indications. Hydrothermal alteration in VMS systems, we have to see which type of alteration is there. So I think that is a very good presentation, and I congratulate all the speakers to enlighten the audience, and thank you very much.
Thank you, respected chairs, for summing up this session so well. I thank all our speakers once again. We now request Shri Soni Kurian, Director, Co-Organizing Secretary, to kindly come up on the stage and present our chairs with a memento in appreciation of their valuable contributions and in recognition of our respect. Thank you so much, Kurian sir. With this, technical session 1 concludes. With great pleasure, I extend our heartfelt thanks to all the participants, speakers, and delegates for making this session truly enriching. You are now invited to proceed for high tea, which has been arranged in the banquet hall on first floor, as we'll now be taking a short break. During this time, we encourage all the participants to visit the poster session, which is being held in the multi-purpose hall on the first floor, and exhibition, which is currently running in the exhibition hall 1 and 2 in the basement. I request you all to kindly gather here by 17 hours so that we may continue with the second technical session. Thank you. Thank you. I'll arrange. Sir, I think we have Gentlemen, it is now time for the keynote address of this session. It is an honor to introduce Dr. Zbigniew Mawlewski, Principal Geologist, Polish Geological Institute, with over 30 years of international experience in geological mapping, modeling, and 3D visualization. A pioneer in using web technologies for disseminating geological information, Dr. Zbigniew Mawlewski initiated the efforts that led to Poland's first country-scale geological model in 2005. He also spearheaded the development of the Geo3D Viewer, an innovative web-based platform for visualizing and sharing geological data. Currently associated with the Polish Geological Institute, he has spent the last decade advancing geological modeling and enhancing accessibility of geoscience information for both scientific communities and wider public. Today, he will be speaking on 3D modeling for geological exploration, case studies by the Polish Geological Institute, National Research Institute. With great pleasure, I invite Dr. Mawlewski to take the stage and begin his talk.
Good afternoon. Director General Shri Asit Saha, Chairmen, esteemed participants. I would like to present the talk on 3D geological modeling for exploration, case studies by Polish Geological Institute. It's a pleasure to be here. Thank you for inviting me to give this presentation. So I'm co-authoring this talk with Dr. Ewa Szynkaruk, who is the chief geomodeler at Polish Geological Institute. So few words about Polish Geological Institute, National Research Institute. It's in accordance with geological and mining law in Poland. PGI fulfills the task of the State Geological Survey in Poland. PGI employs 850 people in main office in Warsaw and 6 regional branches. Among many specialized fields in this research, 3D geological modeling has been present for daily use for last 2 decades. So this map of Poland, I will show it in detail later, and we have 7 places where PGI is operating. So I will present today several models created for various purposes and in different scales. Sorry for typo, it should be off. So we've got models for structural framework and parametric regional models, models for created specifically for hydrogeology, for shallow and deep geothermics, for geohazards, high-resolution models for geoengineering and urban planning, and very nice and funny models for geotourism. So, the biggest model we created is a 3D geological model of Poland. It was created in 2 different eras of geological modeling. 20 years ago, we were pioneering in country scale geological modeling, and we created this model which missed the superficial part. So it started down there at minus 500 meters and went to minus 5,000 meters below sea level. And it was renewed in 2024. Finally, we reached the terrain surface. We used the higher scale and we modeled more layers. So these two models outline the time we do geological modeling in PGI. So to show how big Poland is, I compared it to states of India, and I think the closest state in area, it's MP state, only 4,000 square kilometers smaller than Poland. So this is just for reference what a mid-size country means in my presentation. So to compare how different scales of our countries are. So we create these models as an urgent task ahead to convert our two-dimensional maps into comprehensive 3D models. Almost all Poland is well explored. We have several thousand deep wells drilled for hydrocarbon exploration in the past. So plenty of data, but everything was created in 2D flat maps, not showing in full richness of the geological structures. So it was time to start converting this rich geological data into 3D geological models. And this is one of big initiatives in Poland to convert 2D maps to 3D geological models. So we integrate wealthy of subsurface data because without integration of data we can proceed because different coordinate systems, different units just make it impossible to combine this data into one model. So the integration is most important part prior the 3D geological modeling. So here we see thousands of 2D lines, 2D seismic lines. These lines, this seismic is shallow. It means it reaches 2.5 and 3 kilometers depth. But we also use very deep refraction seismic to penetrate deeper crustal zones. Of course, we have wells, and in this case, I present only 7,000 wells, which are deeper than 1,000 meters, and reach 7,000 meters at the deepest well. And we, of course, use data from geophysical surveying. So in this case, gravimetry and magnetics to delineate important features. Like here we can see a very important part of Poland, geology of Poland, Taser-Tonquist zone, separating Precambrian Eastern European plate from Variscian and Caledonian basement. And more details in high resolution are visible here. So it's not just entire model of Poland. We have plenty of models. Here are listed only 6, but several more are now under development. So these are models for shallow geothermics, for data integration for hydrocarbons, exploration, a model for geohazard related to abandonment of coal mines, which take place in Upper Silesia coal basin. We had 65 coal mines 35 years ago, and now only 6 in operation. So all these abandoned coal mines poses a threat to the surface, both in sinkholes and flash flooding. So here we have a sedimentary basin of Gorzów block created to explore both structures and parameters. And finally, we have high resolution urban geological map down to 20 meters to explore geoengineering conditions for surficial infrastructure. And finally, this is the geotouristic model of one of the geopark in Poland. So what we create brings a new type of context for regional model and well interpretation. We see increased use of our models. Geologists, even from older generation, start to utilize our framework to make more detailed models of regional structures. So this context, which is presented in quite a new way, really impressed users, and we are glad we can provide a so-called game changer for subsurface interpretation. And what is very important in modeling we are doing at PGI, it's uncertainty quantification and risk management. So here we've got two examples what was done in the past. We've got binary uncertainty. We could say that this boundary between two layers is certain, and this dashed line presents uncertain. Nothing else can be done about geological map and uncertainty of its representation. But here in the 3D model, we've got uncertainty coefficient, which present perfectly all presented information. In this case, we created certainty coefficient. The red places are most certain, and what you see at the bottom of the model, we don't know exactly what is there, because the certainty coefficient is equal to 0. So this is a very important part of geomodeling, to be sure that stuff we create and present to public, it's created with certainty. So now we go even to the higher resolution. This is a field scale model for very important minerals, for molybdenum, copper, and tungsten. And it's a very important deposit of these metals on the map of Europe. Today we could see the lecture on Great Britain ores, and here we've got a granitic intrusion, very well mineralized with hydrothermal fluids, providing a lot of scheelite for tungsten in this ore. So we create such models for various purposes. And this is what I said. Also, a very interesting model for geotourism. This is a geopark of Góra Świętej Anny in Poland, and we created 3D geological model of this place just to make people more interested to go there. It's not replacement. We don't sell it as a place you don't need to go. We try to make it even more attractive by presenting geology on the fly. So anyone who uses a smartphone can open this model and get interested by slicing cross sections, drilling virtual boreholes, or just disassembling geology like Lego blocks in web viewer. I will talk about it later. So on the map, which is overlaid of the model, we can locate geo points, and for each point in this geopark, we can present both short description as well as posters which are displayed in reality on the sites. So for making this model accessible for everyone and not to make them die on the hard drives or in the reports, we created interactive and simple web-based viewer. It is made to show these 3D models on the web browser. This is web address, and later at the end of on the next slide, I will present QR code. You can prepare your smartphones to scan QR, and this is something which really open eyes for many people, just to see that geology is not really difficult history, difficult discipline, and everyone can see very exciting, very important features of 3D models, just playing with this in a simple way. Of course, we try to make it as simple as a geological map. So we prepared geological legend and basic functionality like cross sections and virtual boreholes on the right, and everyone can operate by dragging these layers up. And for example, in this case, looking at the bottom of Permian discontinuity, sub-Permian discontinuity, and also present isolines, contours which present the structure of the model even better way. So, looking for the way to present all models created for Poland, we made one globe to show them all. You know this. You know this quote from Lord of the Ring. Now we present all publicly available models around the world in amount of 150 models, which are created in Europe, North America, Australia. And we are looking for other models which can be presented in the same way. So you see on this globe question marks presenting empty spaces like Africa and larger part of Asia. We are looking for publicly available models, 3D models, which can be shared publicly. Of course, these are not models from industry or from private companies, which usually don't share a model for deposits or exploration fields. And this is my kind request. If your geological survey is creating 3D models to public domain, please contact us in this case. And as I promised, this is the QR code, so please scan, open, bookmark, and share with others. It's really worth to see this collection of public 3D models published around the world. So our 3D geological modeling is supported by communities promoting this discipline among geosurveys in Europe and in North America. So European 3D geomodeling community gathers more than 200 geomodelers across Europe, and biannually we make meetings once in Europe, once in North America, These are not competitive organizations. They are supporting each other. We are participating in both meetings. And the last one, the biggest one, was organized in Warsaw in last April. And this was big success, 5 days of hard work to exchange ideas, new frontiers, and just support each other. The group you see here is made mostly of employees of geo surveys across Europe and North America. So I really hope GSI can join these communities in future and share their experience in Geo 3D modeling. We welcome everyone to contact us and join the communities. So in conclusions, I don't want to repeat what I said before, so I would like to present 2 slides, 2 pictures to show that Geo 3D modeling and should be assisting professional geologists in exploration of new domains, not always visible on traditional 2-dimensional maps and cross-sections. So this is a way to solving geological riddles in 3D. And what's more important, in my opinion, that 3D geological models may also bring geology to young minds. Displaying the solid Earth on their smartphones may really fueling their curiosity. So these are very important conclusions regarding 3D geological modeling we are carrying in Poland and across Europe. So thank you very much for your attention, and I hope you can browse the models created in Poland at this website. I really look forward to hear from you. Thank you.
Thank you for your presentation, sir. Now we invite some questions, and these are just questions from the audience.
Yes, you had said 1,000 meter, more than 1,000 meter wells. These are all exploration wells of oil, for oil?
Yes, for hydrocarbons. Yes, Poland was under communism regime during 45 years, and no one counted money for exploration. So huge money went for drilling for nothing, because 95% of these wells were dry, but the drilling campaign went on and on and on, and billions of dollars went for nothing. So now we have data. 7,000 wells, 7,000 wells deeper than 1,000 meters. Most are cored. Yes, this is mostly. Yes, we have great geological core repositories, but of course we've got also a lot of geophysical wire logs. However, you know, 60s, 70s, they were not great tools by Soviet Russia. So the quality of these wireline logs is not perfect, but we try to convert and use them. Yes, most is in semi-detailed, but we are getting more and more detailed surveys in such places like the ore deposit I presented. I don't know the ratio of semi-detailed and high resolution, but yes, everything is covered with gravity. Perhaps 15,000. 15,000 we collected, but there is much more. which are not converted to digital yet. There is many on paper, and we are trying hard to get everything in digital form to be able to use it in this software.
Your software is freeware.
Mm.
It is a Python based tool, huh?
Oh, the Geo3D, it's not yet freeware. It's not open source yet. Believe me, I get this question during every my talk. Everyone wants this software to be open source, but we are trying very hard to make it open source available for everyone. But so far, you can contact us and we can present your models on the fly. Next day, you will see your model online. Well, there is perhaps 1,000 factors which we should take into account. We take several. This is just beginning. Every year, the new paper is presented on geological uncertainty factors, and we are following this. But in most cases, these are uncertainty from distance to data and well deviation unknown. And you know, other factors which are related to surveying. Oh, it's not big. It's 1 kilometer 200 by 700 meters. It's not big one. Oh, okay. So the deepest borehole penetrating tungsten deposit was 1,500 meters. Oh well, it's secret. No, of course, with this amount of data, we can say that it is certainly certain. But we didn't create yet final distribution of this coefficient. We are working on it. It was released in 2024, and now we're trying to make it even better by publishing certainty coefficient. The depth of the model is minus 5 kilometers below sea level. Yes, our refraction seismic can reach 15 kilometers, but this, of course, is very sparse. We don't cover entire country. There are 7 or 8 cross-country deep refraction profiles.
What about your geological mapping scale of entire country? What scale? Surface mapping.
Oh, surface mapping. Poland is covered with 1 to 50,000 scale. Entire country is covered. So we have 1,055 map sheets. And now we are converting it to digital. Almost 70% is already digitized. Yeah.
Can we conclude it? Your presentation. It was very nice.
Thank
now
you.
We can go to next one.
Yes. Thank you.
Okay. Thank you, one. Due to shortage of
Thank
time,
you.
sir.
Thank you, Dr. Malalefshe. Sir, I would humbly request you to kindly remain with us on the stage only. Sir? Sir, it is requested to you to kindly stay with us on the stage. May I now request Shri Asit Saha, Director General, GSI, to kindly come on stage and felicitate Dr. Malalefshe with a memento as a gesture of our gratitude.
Don't drop it. Yes, of course. And this is for as a stand. You know? Yeah. Thank you very much. And the box itself is a connective item. Yes. Thank you. Okay, sir.
Thank you so much, sir. We will now proceed to our technical section. We have a total of 6 presentations here. Before we begin, I respectfully ask all the presenters to remain within their designated time limits to ensure the smooth flow of the program. At this point, I would now like to hand the session over to our chairs. I also request you, sir, to kindly moderate the presentation timings as per the schedule. Over to you, sir.
Actually, this first presentation was very amazing, showing the 3D diagrams. Actually, I have. I also have a curiosity about the. Now we can go to the next presentation by Devika.
Yes, sir.
On categorization of mathematics, we cover the very right over the D exhibition 385. Most audience. Next presenter. Devika Sharma.
Ms. Devika. Yeah, you can start.
Yeah, okay. Very wonderful evening, everyone. My name is Devika Sharma. I'm a project associate at CSIR National Institute of Oceanography, Goa, India. And the title of my presentation is Petrogenesis of Mafic Cells Recovered During the International Ocean Discovery Program, Expedition 385, Guaymas Basin, Gulf of California. And this are the presentation outline, which I'll be going through in a few seconds. So before we talk much more in details about the mafic cell samples from the Guaymas Basin and why we have chosen this particular basin, let us first try to understand how the Gulf of California, which is where this particular basin is located, evolved. So, and in order to do that, let's go back to 40 million years when the Fallopian plate was subducting beneath the North American plate. And there was a divergence between the Pacific plate and the Fallopian plate. So by the time at around 30 million years, the Fallopian plate and the Pacific plate, and along with the North American plate, meets together, which results in the development of the two triple junction, the Mendocino in the north and the Riviera in the south. And with time, by around 20 million years, as this two triple junction migrates away from each other, the subduction of the Fallopian plate ceases completely, which result in the transition from a continental zone boundary to a transform boundary. And by the time of around 12 to 15 million years, or specifically 12.5 million years, with the cessation of the Fallopian plate subduction, the rifting in the Baja California, which was considered to be a part of the North American plate initially, rifted, and spreading started by along with the activation of the San Andreas Fault by around 7 million years back. So this is the present tectonic settings of the present-day Gulf of California, and you can see the series of sword-spreading ridges going along the Gulf region. And our study area is located in the central part of this Gulf region, and where one of this spreading ridge is overlapped. So here comes the questions which everyone must be wondering: why the Guaymas Basin? So the first point is that the spreading in the Guaymas Basin started around 5 million years, which means that it is a very young and actively evolving ocean basin, or an actively rifting ocean basin. So studying this ocean basin or studying the mafic cells of this ocean basin, we'll get to know how the mental processes works and how how the chemical heterogeneities occurs, and during the transition from a young ocean basin towards a mature ocean basin. And the second interesting point about this particular area is that the sedimentation rate is quite high in this region, with an average estimated average rate of around 1.02 meter per kilo year. So which make it a unique settings compared to other mid-oceanic rich settings, and there, where the magma, instead of spreading across the ocean floor, it intrudes within the thick sediments or the massive sediments as a sill. So this is the lithostratigraphy of the site U1546. Our whole interpretation is based from this site U1546, which is located 56 kilometers away from the one of the northern segments of this spreading center. And among the 4 holes drilled at this particular site, only at two holes the seals were recovered, the hole A and hole C, at the depth of around about 354.6 and 348.2 meter below the seafloor at this particular site. And the thickness of this sill is around 75 meter, which you can imagine how very thin compared to the overlying and underlying sediments. So we did the petrography, mineral chemistry, and the whole rock geochemistry analysis. And these are the petrographic results where I'm trying to show that the mafic cells of the Gomas basin are majorly have the characteristic of a typical basaltic rock, which is such as the presence of the clinopyroxene, plagioclase, and olivine we have found, but it's limited to a few samples only, and oxides in some of the samples. And the variation which I'm showing here is that at the top and the bottom contact, we can see the sample is very fine grain, and as we move towards the deeper part, it transitioned from the basaltic to a doleritic and to a gabbroic, and again back to the basaltic. And based on the mineral chemistry data, our data suggests that most of the olivines are phosphoritic with average percentage of around with a range of around 52 to 73%, and most of the clinopyroxene at our samples were the calcic rich, and it straddles between the diopside and the augite. And also the plagioclase were mostly the calcic rich, with few of them falling in the andesine fill. And based on the whole rock geochemistry data, it suggests that our samples, the mafic sill samples, is mostly has this tholeiitic nature, which are typical of a mid-oceanic rich setting with low potassium. And these are the slides which where I want to show how the fractionation patterns occur and which minerals are generally dominant in our region. So as per the fractionation train, what we have observed is that the clinopyroxene are mostly the dominant in this region, followed by the plagioclase. Although we have seen some olivine, but the fractionation of the olivine is very less in this region. And specifically in this plot of MgO versus zirconium, we can see that most of the points or for the overall data cluster together at a particular region, which also from this we can also interpret that the magma source might have been derived from a single source. And another interesting thing about our study is that although we can see the chemistry, the nature of the mid-oceanic rich basalt. Specifically, there is a heterogeneity between the enriched mid-oceanic rich basalt and the normal mid-oceanic basalt. But we can also see that the niobium is highly depleted in this region, like in this primitive multi-element, primitive mental normalized multi-element diagram. And as well as the barium, as well as we can see the positive anomaly of the lead, uranium, and barium in this region, which is typically associated with the subducted slab. So we try to plot whether this particular mafic cells has been contaminated by the barium source or the subducted slab. So the ratios which we found is around 18 to almost 40 and 60 or almost 60. So this indicates the possibility of the subducted slab influence. Although our samples chemistry varies between the enriched and the normal mid-oceanic rich basalt, we try to plot the tectonic discrimination diagram where we can see that most of the samples fall between the normal mid-oceanic rich basalt, which also suggests that the mafic cell samples in our study area might have been sourced from a shallow and a depleted source, and which might have been might have been enriched by the subducting slab. But the question here is that since the sill samples in our study area is very thin compared to the massive sediments, so we try to plot the thorium by niobium plot in order to compare whether the influence, because we need to consider the factor of the sediment influence as well. So in order to compare, in order to know whether this was whether the high barium and the uranium, which is the which is basically an unreliable element, has been enriched in this particular mel. So we found that the thorium and niobium ratio, which is considered was one of the excellent sediments marker. So the ratio is fall above 0.5, which is typically not observed in normal mid-oceanic rich basalt settings. And we have also tried to calculate the pressure and temperature. This calculation is based on the silica-based thermometer from using the whole rock, measure oxide data, and our samples fall between 1,320 to around less than 1,400, which also suggests that the sample, the source might have been from not from a deeper source, but from a shallow source. So in order to conclude the whole story of mine, we are suggesting that this mafic cells might have, the source of this mafic cell might have been from a shallow and a depleted source, but we cannot 100% give you the confirmation that the enrichment of this highly mobile elements is from the subducted slab only and not the sediment influence, because we need to consider the sediment factor as well. For this, this is just the preliminary investigation, and further analysis of our rare earth and isotope studies are still in the process. And thank you.
Okay, thank you. Now the house is open for questions, any queries from the audience, please.
If there's no one else, I would like to ask, basically, not a question, but some information if you can provide. This IODP 385, when was it conducted?
Sir, 2019.
2019. Acha. And one question also, if you are getting a strong MORB affinity, which is suggestive of ocean ridge basalt, ridge process basically, and then the subduction, contamination due to subduction related processes of subducting, which plate is subducting under which plate,
Is there any data on that, or have you thought along those lines? Because these are two contrasting tectonic settings.
Sir, as I have mentioned in my first slide, when I was talking about the evolution of the Gulf of California in this, okay, so the Falerian plate, like before 40 million years, the Falerian plate was subducting beneath the North American plate, and by the time around 30 million years, this Falerian plate, along with the Pacific plate, meets the North American plate, which result in the formation of the triple junction. So there, as per the tectonic evolutionary history, there is a signature of this Falerian plate subduction.
So subduction followed by rifting, you mean to say?
Yeah.
How far are these Guayama basin from that subduction or suture zone? Distance-wise?
Distance-wise, I'm not able to recall the exact.
Achha. Anyway, but because we have to use the chemical plots very judiciously actually. When you plot something, you will definitely get this thing. But if the tectonic data or the field data is not supporting your chemical observation or chemical plots, then you have to think for some other explanation also. You have to think on those lines.
Sir, actually, it's only been about 6 months only since we started this research. So we are still in the process of further analysis.
I am just saying you have to consider these things, keep it in mind while studying further, right?
Okay, thank you.
Thank you.
We can go to the next one.
Okay. Hello. Okay. Good evening, everyone. Today I present the equation state of rutile and CaCl2 type phase of germanium oxide up to 70 GPa. So here is why germanium oxide we have studied. So basically, germanium oxide is actually a good structural and a chemical analog of a silicon oxide. That is a very common mineral in our earth crust as well as mantle. And why I said about is a good chemical analog, the below two lines actually show that the silicate oxide is from rutile type. That's basically the tissue by structure we know. It goes to the CaCl2 type phase around 50 GPa, and this CaCl2 goes to alpha PbO2 type phase around 120 GPa, and this alpha PbO2 type is around 270 GPa. And the same phase transition is actually happen in case of germanium oxide, but lower pressure. Why this lower pressure is important? So on the case of high pressure study, as the pressure is lower, the calibration of the pressure is much accurate. And another thing is that if the pressure is lower, because pressure is inversely proportional to the area, so my sample volume is also increased. And when the sample volume is increased, I can put more thermal insulator in my diamond anvil cell. I just talk about diamond anvil cell. So, and then our heat is not loose from the chamber. This is the first motive to study germanium oxide. And second, from the technological application, these germanium oxide thin films are very much high optical quality that use as a data storage and the information processing. And this rutile here, today I am talking about the rutile to CaCl2 type phase transition. And this rutile to CaCl2 type phase transition is basically a second order phase transition that is also known as actually Landau type phase transition. And this kind of phase transition is basically very much sensitive to what type of pressure transmitting media we use. Okay, and here in this work, we systematically investigate the equation of state of this rutile and CaCl2 type of germanium oxide using our laser heated diamond anvil cell. Along with that, we perform ab initio density functional theory calculation to validate our experimental result. And we feed the volume pressure data of the germanium oxide both using a Landau model and without a Landau model to show how good the Landau model is. And here is a methodology. So basically our starting material is basically a polycrystalline germanium oxide, which is actually a monoclinic alpha quartz structure. And then we use a diamond anvil cell, that's basically a 2 gem quality diamond, and we press inside that to creating high pressure. And then characterize the sample using XRD, and the wavelength is 0.33 Armstrong. And we use pressure calibration by platinum 111 diffraction peak. And our theoretical calculation is performed using density functional theory that is implemented in the quantum espresso package. For treatment, the nuclei, we use the local density approximation and the exchange correlation function, and the electron nuclei interaction will be treated using the non-conserving pseudopotential. And here are some kinetic energy cutoff that we use for this ab initio calculation is 150 Rydberg, and the reciprocal space of the minerals actually sampling by 12 cross 12 cross 12 K point grid. Now come to the result. So here is first is figure 1, it shows the diffraction XRD pattern of the rutile type phase when we use the pressure of 14 GPa and heated the sample 1350 Kelvin and then quenched the sample to room temperature. And here the red bar at the below of the figure is show the rutile type phase peak. And the platinum is basically, the blue line is our pressure calibrate. And the neon is basically we put some hydrostatic media because our earth interior is mostly hydrostatic. So we put some liquid or gas to make the media hydrostatic. So this green is coming from this neon hydrostatic media. And after getting this peak, we fit this spectra by using Rydberg refinement and get the lattice parameter and the volume. And in the next figure, figure 2, we plot the pressure versus lattice parameter plot, and the red one, the solid red one is our experimental data, and the green below solid is our theoretical data. And the other hollow data is basically the previous experimental data or theoretical data. And this shows that as pressure increase, the lattice are actually decrease. That's obvious. But the thing is that the crystal is anisotropic. The 2A and C lattice parameter decreases differently. And if we fit this data, we can find that the A axis is more compressible than the C crystallographic axis. And after getting this A and C lattice parameter, we can easily convert for the tetragonal phase of volume. And similarly, if we plot this volume versus pressure, obviously the volume is also decreased, and again the symbols are the same meaning, and now we fit the data with this equation. That is a very famous equation of Birch-Manon equation of state, where this K0 is basically the isothermal bulk modulus, and K0 prime is the derivative of the bulk modulus, and V0 is the volume at the reference condition. And when we fit this data, we can find out our confidence ellipse of this fitting parameter, that is actually bulk modulus and the pressure derivative of the bulk modulus. And at the red, the solid red one is our experimental data, and the bar is basically our standard deviation, one standard deviation. And you can see the 68% confidence ellipse, there is a hollow line. That's actually basically the independent measurement of the bulk modulus from the ultrasonic measurement. And that's very good agree with our experimental data. And the solid green one is our theoretical data. It is below the confidence ellipse because the theoretical data have no uncertainty, so we have not plot any confidence ellipse from that. And the values for this parameter, fitting parameter, are shown in the table 1. And similar thing, if we do for another sample and heated now, pressurized now around 35 GPa and heating 1580 Kelvin, and again quench to the room temperature and take the XRD pattern, we can found the CaCl2 phase. That's actually showing the again red bar. The asterisk I forgot to mention, the asterisk is basically the starting material. That's our alpha quartz structure. And the green one is basically again the pressure medium, and the blue one is our pressure transmitting, pressure calibration. And similar thing is actually do, basically this rutyl to CaCl2 type structure transition is basically a orthorhombic distortion of the tetragonal structure. So you can see in the XRD pattern that the H scale, that's like 1 to 1, this peak are actually split in this CaCl2 type phase. Like 2 1 1, this peak is actually split into 2, 2 1 1 and 1 to 1, because now H is not equal to K in the orthorhombic phase. And again similar things with, if we treat with this phase, we can get the lattice parameter plot, and again here you also see that the 3 lattice parameter are not equally goes. They have anisotropic behavior, and the most compressible axis is the B because it go more, and the least compressible axis is the A crystallographic axis. And the similar treatment with the volume pressure equation of state for the CHCl2 type phase with the Boltzmann equation of state, and here our fitting parameter is volume and pressure. And if we do that, we have getting our confidence ellipse. And again, another thing is that the two fitting parameter have negative correlation, means if we increase the one, another one decrease. And here also it's a good match with the previous independent measurement. And here is actually the table for the fitting parameter of the CaCl2 type phase. Now, though I said that this is a second order phase transition, and second order phase transition have a very characteristic property that its volume with pressure is not drop. It is a continuous phase transition. So, and this kind of phase transition has a very high symmetry breaking strain that actually expressed in terms of these spontaneous strain that I write in this equation E1, E2 and E3. And where this A is the lattice parameter for the orthorhombic phase or the high pressure phase, and A0 is the lattice parameter for the high symmetry phase or the rutyl type phase in the stability field of the CaCl2 type phase. And if we calculate this E1 minus E2 square, that is the symmetry breaking strain with respect to this pressure minus transition pressure, is basically for a second order transition is a linear. And as we see, both for our experimental and computational data, where it touched the 0 line is basically the phase transition pressure from this rutyl to the CaCl2 type phase. From our experimental data, it is coming around 30 GPa, and from our computational data, it's coming around 23 GPa. And now, when we get this transition pressure data, we can do the Landau fitting for our whole data from 0 to 70 GPa. That's our pressure examine. So here, as you see, that that's the whole data from 0 to 70 GPa. And here we use very simplified Landau model. So first equation is basically signify how the low pressure volume is equal to the, the low symmetry volume is equal to the high symmetry volume with a EV. EV is basically the volume strain, and the volume strain can be expressed as a power law like A modulus of Pt minus P to the power B, where B is actually exponential factor which depend on the phase transition, is basically 1 for a second order phase transition, and its value vary from 1 to 1 by 8. And the A is basically a scaling parameter, that's we call strain scaling parameter. A value is negative, means our high symmetry phase has a lower volume than the high pressure phase actually lower volume, and if A is positive, then our high pressure phase will be higher volume. And we already know the phase transition pressure, and if we do this in our code, and the solid line is basically our Landau fit, and the dotted line is basically without Landau fit. And that same treatment is doing for the computational data. And why our Landau type fit is a good fit with respect to our normal fit is basically examined by this P obs minus P calculated plot. P obs means basically the observation pressure at a particular volume, and P cal is basically calculated from this equation of state line, that the solid line. And if you look at this data, where the diamond shape, solid diamond, are solid are the Landau fit and the hollow are the without Landau, and the diamond is for the computational and the circle is for the experimental data. And as you see that the P obs minus P cal is decrease for the Landau type phase, and it's eventually decrease at the transition pressure. The vertical lines at the transition pressure are shown. And last I conclude that after fitting this result, I can found this parameter, that's the Landau fitting parameter, where this Pt is basically the transition pressure parameter, AL and BL are the already I told AL should be negative because our high pressure phase is the lower volume, so it's a negative. That's the strain scaling parameter, and B is basically the power law that taken 1 because it's a second order phase transition, and the other parameter are keeping fixed. And together this study and our previous study is basically constrained these 4 phase that I told, that the rutile type, CaCl2 type, alpha PbO2 and PA bar 3 type phase are actually constrained into 120 GPa with using a single pressure transmitting media, that is neon, and the single pressure scale, that is platinum. And as the GO2, Germania, is below the periodic tables, below the silica, so it has a larger volume than the silica, so it has a larger volume than the SiO2, and corresponding its bulk modulus will be decreased, and that's the result that's below. And again, here we constrained our here due to the study for the up to 70 GPa, these 2 phase are basically more constrained for this pressure range. And these are the reference I use for making this presentation, and thank you. If there is any question. Yes, sir. Yes, sir. No, sir. Yes, sir. It is actually related to Earth interior. We have to investigate what happened inside the Earth. So because we have trying to investigate the phase transition. So not exactly mineralization, but it's help to industry because it's the germanium oxide is a very high optical property. So it can be used as a data storage purpose. So its high pressure study is important for that purpose. So this has a industrial implication.
The kind of rutile which we are having in India, or especially in Gujarat, along with the Deccan traps, you have taken rutile from there?
No, sir. We have taken germanium oxide in the rutile type phase, means the structure is the rutile type. Yes, not the rutile, TiO2. We not take TiO2, it is GO2. Yes, sir.
In a new term.
Yes.
So, but again, basically this particular seminar links to everything, to the societal causes or something. So that's why the question. Thank you very much.
Thank you, sir. Thank you, sir.
I just have one query.
Yes,
it's not a question actually. So it is obviously a high pressure laboratory simulation or experimental work.
Yes, sir.
So for the deep under the
Yes,
earth. So what happened? Is there any such work on perovskite structure or like that? CaTiO2 and it is
I cannot get the. I cannot.
Perovskite structure.
Yes, sir. Yes, sir. Perovskite is basically a very famous for high pressure study.
Yeah. That's why.
Because it's actually a solar cell nowadays are used perovskite. Yes. We actually in our lab we also study perovskite because the Earth we go beyond the post perovskite, right? In our Earth the highest phase we encounter the core mantle boundary, that's the post perovskite, right?
Yeah.
But for highest pressure we can be. We computationally found that it may be beyond post perovskite.
Yeah.
So yes, that's for perovskite is also studied.
Okay.
Okay. Thank you, sir. Thank you. Yes, sir. Yes, sir. Yes, sir. Yeah.
So is it possible that your studies can help us to target its finding in other mineral systems?
Then in that case, sir, we have to find the affinity of this particular element in these high pressure phases. If we get that, means combined with this data, if we find the seismic data, because we have get the bulk modulus from this data, and if do the seismic one, so you can get the VP and VOSA velocity, so you can find that.
You are showing two models, rutile model and calcium CaCl2 model.
Yes, sir,
two types
CaCl2
of
is
models,
actually
na?
high pressure phase, so it's
Huh.
we get beyond 30 GPa. So in our earth pressure, we not go beyond 30 GPa crustal, right? So we found below 30 GPa. So most stable phase then will be the rutile type phase at that case.
Any other question from audience?
Dr. Ghosh,
Yeah.
talking about the natural occurrence, usually in geological parlance, this you have done the experimentation work using only the pressure, kind of generating the pressure
Yes,
30 GPa.
pressure.
What about temperature? Have you also tried that?
Yes, yes, sir. I can
Because-
address this question. The pressure handling is temperature handling is little bit difficult. So we done all the experiment in the room temperature. With all the experiment will be room temperature. So we can only use this for 300 Kelvin, for not for the high temperature.
Not for the high temperature.
Yes, sir. Not for the high temperature.
Okay.
But we can do that. We can do that, but this is challenging. High pressure, high temperature, challenging.
Plus, you have been using a closed system.
Yeah, closed system.
Whatever you are putting in.
Yeah, closed system.
Which is unlike the natural.
Unlike the natural system, but yeah, unlike the natural system. But
Okay, thank you. Thank you very
sir.
much.
Thank you, sir.
Thank you. Now we can go to the next one. High temperature.
The next presentation will be on high temperature phase transition in serpentine by R. Valli Divya and Rajakrishna Datta.
No, I can anyway. Yes, I can do the mic. Where is the presentation? Where is the mouse? Excuse me. Laptop's not working. So just give us a moment, sir.
The mouse pad is not working actually.
ये होगा ये भी
Ms. Divya,
Yes.
also please stick to the time because we are running short of time. We have to finish it within time.
So good evening, everyone. So my topic is high temperature phase transitions in serpentine. So first we know about serpentine. So what is happening in ultramafic rocks? They undergo serpentinization to form serpentine, loosely from olivine. It reacts with water to form serpentine and brucite. Brucite also reacts with silicon dioxide and gives rise to serpentine and magnesite. So orthopyroxene also converts to serpentine. So this process is termed as serpentinization. So we will look at the tectonic settings in which serpentine occurs. So hydrothermal fluids, when they in the ridge axis, that is mid-oceanic ridges, where wherever olivine is there, the ultramafic rocks, it interacts with the hydrothermal fluids, the serpentinization is going to happen. So we are also in abyssal peridotites, also triggered by faults.
serpentinization induced by normal faults where subduction is happening. In subduction, there is two things happening simultaneously. One, serpentinization is forming at the but when you go in deep interior, the plate is subducting. Dehydration of water from serpentine occurs. So that will convert, they cause phase transition in serpentine. So the methodology applied was, I took a serpentine sample, then we did powder using mortar and pestle. So since I'm doing it high temperatures, so we use the muffled furnace. So then we used powder XRD. So all the powder XRD has been done. First, we need to characterize anything starting, we have to characterize using XRD. First, we need to know what the material is. So first we did for the serpentine raw sample. So we found that it is from two databases I matched it, Roof database and which is Raman XRD chemistry database, and ICDD is International Center for Diffraction Data. ICDD database, it shows that serpentine has three varieties, lizarded, antigorite, chrysotile. So this matches mostly with lizarded and chrysotile, but it's a caution because the XRD pattern of all this lizarded, antigorite, chrysotile is very close. So we cannot easily distinguish, and no one has, it is being a challenge to distinguish using XRD, but we know all the, but it is a serpentine mineral that we can do, but the variety is difficult. So people have done Raman also and try to distinguish it. So it's a kind of challenge in this mineral community to identify the varieties differently. So basically this is how people in most of the publications, if you see, what they do is that they keep the time fixed like 4 hours and they heat it at different temperatures, like I heated it from 350 to 1000 degrees. So if you see at 500 the phosphate starts, beginning formation of phosphate starts, and phosphate completely forms around 600 degrees Celsius. At 700 phosphate as well as N-state, the N-state peaks are marked with star, so N-state peaks also starts coming out. But here I kept the time constant. So what my motivation was, I will vary the time at the time of heating. Let's see what happens. So now 300 and 400 degrees Celsius, and we don't see any change up to 24 hours of heating. No, the XRD pattern remains the same, it's serpentine and no phase transition is happening. Then at 500 the phase transition starts, and it is like phosphate peaks after 3 hours of heating, we are seeing phosphate peaks, and 30 minutes the heating is not efficient, hence it remains as serpentine. So if you see, when we are varying the time, we are seeing a different picture than keeping the time unchanged, and most of the publications, they usually keep the time fixed. They either heat at 4 hours, 6 hours, 7 hours, they keep it fixed for finding these phase transitions. Then if we heat at 600, complete phosphate peak starts at 4 hours of heating. N-state, interesting part, N-state starts at 600, but the diagram which I showed before, there 4 hours of heating, N-state starts at 700 degrees Celsius. So if you see, when we are heating at 8 hours at 600 degrees Celsius, we are seeing N-state occurring earlier at 600 degrees Celsius. So this changes how we view phase transitions. 700, 800, completely it forms phosphate and N-state. That's why I've also, that is from the Roof database, the phosphate and N-state. Others are from up to 24 hours of heating. So we are serpentine is converting into phosphate and N-state only. So what I'm concluding is that I put a temperature versus time graph. So up to 500 we are seeing only serpentine. 500 to 600 phosphate is coming, but after that we are seeing phosphate N-state. What is different is that we are seeing earlier phase transition serpentine when we take the factor of time of heating. So what is the significance is that we know phase transitions, they take pressure versus pressure versus temperature graph, or pressure versus composition graph, or time temperature versus composition graph. But when we include time, the phase transition is going to change. It will become 3-dimensional modeling. But how can we vary pressure, temperature and time together? That is very difficult to do experimentally. Either we can vary either we can do pressure and temperature, we can vary together, or we can vary composition and temperature, we can vary. But if we include time, the whole phase transition is going to change. The picture of phase transitions is going to change. So, but that is quite complex to do, and with our present like logistical, like instrumentation and logistics, it is quite difficult to do. But what I did at room pressure, and I just varied the time and temperature and did one graph. So there a lot more work needs to be done in this, and this can be the future of like studying about phase transitions. It is all because of thermodynamics. If you look at it, it's all because of the kinetics of the reaction. So that all depends on the enthalpy, entropy. So that much details needs to be studied more. Thank you.
Any questions from the audience?
Something. Have you done any enthalpy studies on the phase transformation?
No,
Phase transformation.
Yes. No, I have not done enthalpy studies till now. We are just showing it experimentally. We are experimentally have done enthalpy, like people who are very good in thermodynamics. Like there are some people who are very expert in that. Then we have to do calculations actually.
So do you do this number of hours studies? How many time?
Yes.
It will form into another phase.
This hour study I did up to 24 hours because our limitation is up to 72 hours some furnace can heat. But what is that if we have to go further, why this phase transition appearing early, that can be explained through thermodynamics, but that much expertise I don't have.
Okay, thank you. Any other question from the audience?
Sir, I just have one question. It's a very good experimental work, obviously, in the laboratory framework.
Yes.
Now, the thing is that as you are telling about the thermodynamics, it's a three-dimensional P, T, and T.
Yes.
Capital T. Okay, it is okay. But another dimension is also there, which is very much we have seen in our this geologic period.
Yes.
That is the fluid, you know.
Yes.
That is the F.
Yes.
So it is very, very important to have the fluid also.
Yes.
Because for the serpentine, actually, you have taken one serpentine and then you have heated it up.
Yes.
Now we are having within this 500, 450 degrees centigrade, three transformations of formations of serpentines are there.
Yes.
One is the low temperature chrysotile, then your this liardite, and then your is antigonite.
Yes, yes.
So these things are there. So there is a, obviously what Sarah was telling, say this is a transformation change over there. And what we have seen in our ophiolite belts, that is olivine and orthopyroxene rich, particularly this peridotite or this ultramafics, there we are seeing number of changes of the serpentines with these three phases, and with that increase in temperature and pressure, and if this is also constant, T also constant, but fluid has a great role in this. So P, T, and F. As it is a hydrous one, as you are telling, brucite also there, your serpentines are there. So it's a great role there. So I request to include it in your thermodynamic calculation, F horizon also.
Yes. Thank you. Thank you.
Thank you for presentation. Next presentation will be by Manjari Pathak et al. On discovery and characterization of calc-alkaline lamprophile from western margin of Delhi Fault Belt, Didwana.
Good evening, everyone. I have brought this presentation which reports a calc-alkaline lamprophile from a largely covered area of Delhi Fault Belt. Lamprophile clan of rock is not a cup of my tea. Instead, yet I am presenting here it because of its vast significance in understanding the geomagnetic, geodynamic and tectonomagnetic geodynamic and tectonomagnetic significance of any area. Actually, lamprophile presents a very small volume of any magnetic rock, of the magnetic rock of Earth, but it is a window to know the deep-seated mantle processes. Before going in detail, I would like to inform you that this area is actually recently studied in last few years, which covers the westernmost part of the Delhi fold belt in the Didwana districts. It is largely covered and hardly have 10% of exposures. And actually it is in between. I'm not able to see the pointer here. Actually, the study area lies between the North Delhi fold belt and South Delhi fold belt, which is covered, and the geological information, the tectonic setting of this area is not much studied earlier. So finding of a lamprophile from this region can reveal the deep-seated processes, its implication in the geodynamic settings. So this work has been being discussed in this geological forum. As we can see, the Rao et al. Has compiled the lamprophile occurrences from the Indian Shield, and the calcaline lamprophiles have been reported from the Eastern Dharwar Craton and a few lamprophiles from the Siddhi area of the central CITZ. And the lamprophile from the Delhi fold belt is reported from the Sirohi area, and which is of metal lamprophile affinity. So this work is reports the lamprophile from at the junction of North Delhi and South Delhi fold belt. Before going in detail, as we have seen in the earlier slide, that most of the area is covered by the quaternary and a few outcrops. To know the geology, the predictive geology has been attempted using the geophysical data sets and the study of borewell chips, sludges to know the deep-seated rocks in this covered terrain. We can see the first map is the gravity map of the area, which is showing a low gravity zone in the eastern part of the area. Actually, it is defining the Delhi domain, and the western part is actually the Marwar sedimentary basin lying over the Delhi domain. The regional fabrics of the Delhi domain can be seen in the aeromagnetic maps, where the northeast southwest linear features can be seen. Based on the predictive geological mapping, we found that this area has actually a large belt of granitic intrusion, nearly 100 kilometer long and 40 kilometer wide granitic belt, having various type of granitic types, particularly calcalcaline and peraluminous type. So while validating the geophysical anomalies during the predictive geological mapping, we observed a northwest-southeast deflection in the gravity. We can see here we can see here a nosing, northwest-southeast nosing in the gravity data corroborated with the break in the magnetic anomaly. While checking this gap, this nosing, this deflection in the gravity data, we observed that there is a small outcrop representing the intercalated sequence of quartzite and carbonaceous phyllite. There are multiple intrusions of mafic dikes orienting in the northwest-southeast direction. While studying these dikes, we observed that some of the dikes have the porphyritic appearance with mica as a dominant phenocristic nature. So the first appearance of this in the field suggests that this is a lamprophilic rock, because mica is the most phenocristic phase. While studying this dike in the petrography, we observed that it actually comprised of porphyritic phlogopites and as well as the phenocryst and present in the ground mass, while the ground mass is mostly comprised of K feldspar associated with some apatite and ilmenite and rutiles. So the basic composition, the mineral assemblies of phlogopite and K feldspar itself suggested that it is a minute, a variety of calcaline lamprophile. So to confirm this, we use the mineral chemical data of biotite, and we observed that while comparing this, the composition of phlogopite from the global data of minute, we observed that it sync with it correspond to the calc-alkaline affinity, particularly of minute composition, and the whole rock data, actually I have only the major oxide data right now of this Lamprophire. It also corresponds while comparing with the existing Lamprophoric dikes of Indian shale and worldwide. It corresponds to the calc-alkaline affinity. Now, if we see the geology of the western India, particularly the Delhi orogeny, so Delhi orogeny closed around 1 GA, and now we have a challenge to know, based on the field observations, based on the mineralogical observations, we have to correlate this Lamprophire activity with respect to time, temporal and spatial distribution. So if we compare, we see the Lamprophoric activity in the Indian shale. The most of the alkaline or ultramafic Lamprophires are rift related, particularly of Deccan magmatism. So calc-alkaline nature signifies the subduction related tectonic rhythm. So if we correlate with the near about the orogenic activity, we found that the Sendra-Ambaji granitoids, which are of calc-alkalic origin, may extend that tectonic regime extends to further north, and this Lamprophire may be correlated with the Delhi orogeny. It may be younger too, but for that we need some more isotopic and geochronological studies. Now, Lamprophire also have implications on the mineralizations. Globally, with the spatial and Lamprophire have been correlated with the spatial and temporal distribution of gold and tungsten mineralization. Actually, Lamprophire, if we see this map from the western part of this area, which is largely covered, we can see the Tosham belt in the Haryana and the Degana belt, which is known for the tungsten, and the Balda known for tungsten, and further in the Gujarat, the Nadri location known for the tin tungsten mineralization. There is a nearly 600-kilometer long belt, particularly having the occurrences of rare metals mineralization. And the predictive geology also have revealed granitic belt of nearly 100 kilometers in this area. So this Lamprophire finding actually must be studied in future in detail to know its relation with its regional relation with the mineralization present in this belt. Actually, the Lamprophire is present in the Sirohi belt from the South Delhi fold belt. Now, this work reports the Lamprophire from the junction of North and South Delhi fold belt, and well within this rare metal, 600-kilometer long rare metal belt. So we need to study this Lamprophire in detail to know its significance in the tectonomagmatic evolution of the westernmost part of the Delhi fold belt, as well as the mineralization implications. So now I conclude that this work reports the calc-alkaline Lamprophire in Delhi fold belt area in the largely covered terrain, and its reporting signifies the convergent margin setting in the studied area. It may be correlated to the Delhi orogeny and related to calc-alkaline granitic magmatism, and the deep northwest-southeast structures actually identified in the geophysical map, acted as the conduit for this emplacement of this Lamprophire, and the role of this calc-alkaline Lamprophire need to be studied in future for getting its implications in the rare metal as well as gold mineralization. Recently, we completed a borehole in Didwana for graphite, and some of the gold have been observed in the microscopic levels, though the chemical results are not supported. But these small findings from a largely covered area, which has the very least geological information, such small findings can add for better geological study in future. Thank you.
Thank you. Is there any?
Sir.
Ms. Manjari, very nice presentation actually, but your observation कहाँ देख रही है? अच्छा मैं पूछ रहा हूँ.
Yes, sir. I'm here. Yes.
अच्छा, okay.
Sorry, sir.
नहीं it's okay. आवाज़ कहाँ से आ रही है पता नहीं, speakers जहाँ पे रखे होंगे.
Yes.
Good presentation and good finding also, particularly because most of the area is covered. So you caught it, it is good, but only one small suggestion that just the occurrence of Lamprey does not suggest any subduction related tectonic setting. They are known from stable cratonic areas also. Many parts of India have reported lamprophires, lamproids, kimberlites also from stable cratonic blocks. So just the occurrence of lamprophire doesn't require any subduction related setting. You definitely, it is a very interesting this thing. It requires further studies, but to relate it to subduction, I think is a little far-fetched and too early.
Thank you, sir.
Then we can push to the next presentation by Sri Bhuvan K. Tamta and et al. On weak geomagnetic field during Deccan volcanism, possible link to elevated core mantle boundary, heat flux, and termination of the Cretaceous normal supercross.
Sir, one question, sir.
One query from the audience.
Sir,
I think
please.
also.
Sir, you are showing gravity map of Delhi fold belt, madam.
Yes, sir.
Generally, gravity map data over the Marwar basin can show the low compared to Delhi fold belt. But you know, your map showing high.
Can you repeat, sir, please?
Marwar basin
Yes.
is contain the gravity low generally. That is basin. Okay, that's why we are getting the gravity low. But in your map, it is showing the gravity high. Just to check that one. That is gravity map or derivative map, we don't know. Title.
It is the first vertical derivative map of the gravity data, NGPM data.
Okay.
And in fact, the Marwar basin is showing the high gravity compared to the Delhi domain. And it may be due to the emplacement of vast granitic system.
Okay, you can add for your prospective geological mapping.
Yes, sir.
You can add for Euler depth solutions.
Yes, sir.
Of gravity data or airborne data. By Euler depth, you can estimate at what depth your lamproids are located. That you can correlate.
Yes, sir. We will try.
Okay. Thank you.
Thank you, sir.
Okay, next presentation by Bhuvan K. Tamta.
Good evening to all.
Excuse me, could you please check this? Cursor is not there.
मैम तक ये बड़ा होगा
This will remain like
Okay.
this, but it will appear here.
Good evening to all. My name is Tamta Bhuvan Kumar, PhD scholar from Central University of Punjab, So today here I am presenting the evidence of the weak earth magnetic field during the Deccan volcanic province and its linkage to the Coromantine boundary heat flux and intermission of the CNS. This is now supercon. Supercon is a magnetic polarity which lasts for more than 10 million years. So as you all know, Deccan volcanic province is one of the largest igneous provinces in the world. It is formed by the multiple activity, had a huge impact on the climate, tectonic and geodynamic. Despite the several decades of work on the DEP, like geochemical, geological, paleometrism, and other, there is a very less information about the paleofield. Paleofield is a past Earth magnetic field record and the VDM study. So why we need paleofield study? Because paleofield is only the a direct way to study the Earth 30 processes like Coromantine boundary process and heat flux, this kind of thing. There is only one study done by the Radhakrishnan et al. In 2020, and he first reported the Earth magnetic fields were very low during the Deccan volcanic province. So present work is inspired from this work, and we are conducted the paleofield and a video study from the Mandala Vista Deccan volcanic province. So Mandala Vista comprises of the 37 lava flow. As you can see here, there is a distribution 37 lava flow. So why we choose the Mandala? Because there is already there is a flow by flow magnetic. There is a availability of the flow by flow magnetic data from the Patak et al. And from study the Mandala, we can easily correlate the paleofield value from the eastern DP and western DP. So we can say, so we can check that the magnetic field scenario is same for both the province or not. And the third one is like the younger age of Mandala make us a chance to study the Earth magnetic field recording the last of the Deccan volcanic province. So the magnetic field, to getting the primary magnetic field, the magnetic intensity data was iterated through the thermal and alternate field demagnetization, and for getting the and further for getting the reliable database, we choose these three selection criteria. First, there should be more than 4 points on this digital plot with stable field, and for the stable field, we keep the maximum angular deviation less than 15, and in cone of confidence angle less than 15, which indicate the uncertainty of the data. In clustering of the data, data should be high. So after applying this criteria, out of the 184 specimen treated through this criteria, only 60% specimen qualified this criteria. And but after getting the level paleofield, for comparing the median value from like one location to other location, it is very important to convert this value into the equivalent partial dipole moment, because as we know, the magnetic field value is very low at the equator and very high at the pole, so we can't correlate directly. For that we want this VDM. So after calculating this VDM value, we get a very low paleofield and VDM. As you can see here, there is only 6.7 and 1.58, which is very low to the presented Earth magnetic field, which is not visible with this cursor. And this value is very much with the previous study done by the Radhakrishnan et al. So this indicate that there is a there was a very low magnetic field during the Deccan volcanic province. And this is a mean value. but here we plotted the a flow by flow VDM value for 37 lava flow, along with the polarity recorded in this lava flow, like normal, intermediate, and reverse polarity. From this plot, we can see that there is a in the intermediate polarity lasts for the more than 8 lava flow, and which also have a VDM value is very quite low as compared to these two polarity, which indicate that during the lava eruption, the polarity transfer from normal to reverse for was no sudden. There was a gradual process, and this value, and after and for collection of the VD value from the Deccan Wave volcanic province with the global database, which use the PNT database, like paleontology database from the global database for a time period of 45 to 140 million years. And for the we also compared it with the reversal frequency. For reversal frequency, as you can see here, here is no reversal, here is no change in the reversal for the long period of time, which indicating the low reversal frequency. Here you can see there is a large version which indicating the high reversal frequency. So after the correlation, we seen that there is inverse correlation. There is inverse correlation between the VDM, which is indicated by the orange color, and the reversal frequency. As you can see here, there is a very low reversal frequency, for more than 20 million, there is only one frequency, and there is a very high VDM. And after the termination of the CNS, there is a decrease of the VDM value and increase of the reversal frequency. This indicates that there is a inverse correlation between the VDM and reversal frequency. And second pattern, what we have observed is that there is a stable magnetic field which is known as CNS. And after the termination of CNS, there is an increase of reversal frequency and weakening of the magnetic field, which indicates that there is a destabilization of the magnetic field process, like Jordan wave process. And after the approximately 58 million years, there is occurrence of the DP taken place. So this kind of pattern is also observed in the geological past. Like as you can see here here in the approximately 490 to 460 million approx, there is a more long reverse supercurrent, which is followed by the there is a supercurrent. There is a no polarity. This indicated by the polarity. This indicating polarity reversal. So there is a very low polarity reversal. After the termination of this supercurrent, there is increase of reversal frequency and occurrence of the of the LIP process. Same for the Kiyaman also, there is a very low reversal frequency, and after the moment of this, there is increase of reversal frequency and occurrence of the Mnesin and the Siberian trap. Same for the Reckon also. To understand these processes, we all know this, like formation of the mantle plume and earth morphology is regulated by the deep earth chromatic body processes. For that, we compare the chromatic body heat flux with this blue curve. So after this correlation, what I have find that during the stable supercurrent, there is a during the stable supercurrent, the heat flux was very low, and after the termination of season, the heat flux is increasing, and reversal frequency also increasing, and there is occurrence of LP process. Same for here also. Same for here also. These all scenarios also studied by the previous worker based on the mathematical and computational simulation, and this all can indicate that after the termination of the series, after the termination of the CNS, there is an increase of same heat flux, which is indicated by the blue curve, and geodynamo destabilization, which is indicated by the weakening and earthfall and the increase of reversal frequency, and stability of the double prime layer, which is studied at the top of the outer core, and this instability lead to the growth of the superplume and formation of the LIP. To understand this process and scenario, we formulate two models from the methane also. And Hercules says is that this scenario indicating the stable cone, where the heat flow is very low and there is no D layer stability and there is no superclone. Superclone and this is indicated by these superclone. And after the termination of CNS indicated by this figure, where you see that there is an increase of heat flux and there is a formation of the there is instability in the D double prime layer and formation of the superclone layer, and will lead to the growth of the formation of LIP. For Deccan volcanic province, these questions are also supported by the when this author link the formation of the reunion hotspot with the thermochemical pile which is located at beneath the Africa, which is known as the African large low survey velocity province. So this is all study. So from this I can conclude that during the DP there is a very low magnetic field and there is inverse correlation between the medium and its frequency, but sometimes it is not applicable to all the past. And during the DP there is a magnetic field transition was sudden, not sudden, it was a gradual process, and there is a cause and effect also between these all parameters like termination of the CNS, increase of CMB flux and weakening of magnetic field and increase of reversal frequency. Thank you, sir.
The house is open for the audience. Any suggestion, any queries and questions from the officers present?
There are no questions. I will ask something. Just a clarification, actually. You have decided, you have taken your basalt samples from Mandla Low, isn't it?
Yes, sir.
You said there are 37 flows.
Yes, sir.
Identified by whom? Who has identified all those?
All, sir. Sir, reference is given.
You yourself have mapped these or someone else? Patnaik and Sriram. So, from 1999, you collected samples in?
Sir, ये 2016 approx. Sir, data we have used is from the Pathak et al.
Large scale map उनका available है for delineating different flows.
Yes, sir.
अच्छा, it is available.
Sir, based on petrological, geochemical and trace element study, they have classified lava into the different chemical affinities.
Exposures है enough.
Yes, sir.
अच्छा. And where did you carry out your experimental work? जो measurement of area में?
Sir, IIG Illahabad. University of Geometry in Illahabad, Prayagraj. Yes, sir.
These Patnaik and Srivastava are both from DU, Delhi University.
No, sir, we was from Patnaik sir was from DU, and Pathak sir is my guide, supervisor. Yes, sir.
JP Srivastava is also from
DU, sir. Delhi University, sir. So this, yes, sir.
Talking about this core and mantle border boundary. Is it possible that the upper mantle may be the source of the basalt? How it is different from that composition, and in your area, in your talk, you are focusing on the source from the lower mantle and upper core. How both the compositions are different?
Recent studies are done by the sir Bakula et al. Sir, he did sir tungsten study. And there is sir Ghosh et al. So these both works are published in 2025, and they both have confirmed that the source of the plume was from the deep-seated chromatal boundary. And after the rising of the plume, they are stable at the 660 kilometer. No, sir, but recently, sir, these two study published in good journal. They both are saying that this plume is coming from the deep source.
You can discuss with sir later on also. Okay, let us move to the next presentation because we are already slightly out of time now. The next presentation will be by Sivaji Lahiri, and Sachin Kumar on microscale pore heterogeneity development in mudstone under burial compaction.
Sir, we have not received their PPT. I would also request this presenter to please kindly come forward. Sir, I think they are not here.
So they are not here. That will save us some time, and then we will be in time also.
Yes, sir. Sir, now I would request you both to kindly summarize this session.
During this presentation session, out of 7, 6 presentations were successfully presented by the presenters. There is a variation in presentation. First, regarding 3D modeling from the Italy, Polis Geological Institute. It was a best compilation done by Dr. Mela Lipsje. It was a good compilation actually on different thematic labels, layers, aspects. Second presentation by Devika, K. Devika on Mafic sales. And presentation by Sumit Ghosh is also very good on rutile. But it is a thermodynamics presentation on mineral physics. Its application for geology, it needs some highlight from that institute. The presentation by R.V. Divya on high temperature and serpentine presentation and different variation of serpentine and its different variation showing the composition, phosphorite and ancetite. This highlighting that at 700 degree temperature, two phases, ancetite and phosphorite exist, and later they are also highlighting some other variation at different temperatures. As they have highlighted, they may go for other type of studies. Regarding the next presentation by Manjari Pathak Madam on the calc-alkaline land profiles in Didwana area. This presentation was also good, but the terrain Didwana to Digana is known for this tin tungsten mineralization. There is no particular ore load in that area. So this predictive geological mapping project was taken, and the geophysical data was highlighted. With this, they are covering their theme. And B.K. Tamta, highlighting the geomagnetic field of Deccan volcanics. They are doing their present studies under their different supervisors from Punjab University and Delhi University. Their themes are different, but they also need some geological application and some improvement in that. The next last presentation on micro scale by Shivaji Rao is absent here. So during this discussion, all the presentations and all the interaction during the queries were good. Rest, I hope, for some comments from our co-chairman.
Thank you. So I would take this opportunity to thank the organizers for giving me this opportunity to participate in this 175 years celebration of GSI. A very good organization also, I would say. And today's session, the geodynamic cradles in the depths of solid earth, is really relevant to the studies GSI has been carrying out. As we all know, the geodynamic studies pertain to a study of Earth's processes, their causes or driving mechanisms, and as well as the end results of that process. The initial idea or initial task of the geologist is to unravel or go backwards from the end results to the processes deep inside the earth. They are not visible, so indirect means have to be used. There were, like Sir has excellently summarized all the presentations. I congratulate all the presenters as well as the patient audience which waited very patiently for this session to end. And I don't know, I can say something. Definitely some of the presentations were experimentally oriented and need to find applications in real-time geology or real geology for mineral exploration as well as otherwise. So that aspect should also be covered. Even while doing the experiments, we have to keep it in mind that this has to be applied to real life solutions. That's all I think. Thank you very much.
Thank you, sir, for your kind words. I now request Shri M.N. Praveen, Deputy Director General GSI, to kindly come on stage to felicitate our respected chairs. Thank you so much, sir. Ladies and gentlemen, as we conclude the proceedings of the day, I extend my heartfelt appreciation to all the participants, speakers, and delegates for making today's session truly enriching. We now warmly invite you to immerse yourself in a vibrant celebration of India's cultural heritage. Please join us for the cultural program at the main auditorium featuring traditional folk dance and music. The celebration is to be followed by dinner arranged in the conventional hall. We look forward to your gracious presence. With the same spirit of enthusiasm, we eagerly look forward to reconvene tomorrow, embracing new opportunities for learning and knowledge exchange in the next sessions of this seminar. Thank you all for your valuable participation. Wishing you an enjoyable evening ahead. Namaskar.
Namaskar, madam, and thank you all. Thank you, you too. And thank you, team member.